Hello, good evening, everyone.
Good evening, sir.
I can see a very low attendance today. What's the problem? Any issues?
No, sir, there was a sessions going on.
Which one?
Mad one and mad.
Okay, from 6 to 8.
Yes, sir.
Okay, fine. Okay, so today is the week 3 open session, right? So, have you watched the lectures?
Yes, sir.
All of you? Okay,
Yes, sir.
yeah. So, I think the broader topics are what are the fundamental subspaces, right? And I think least square and projection methods, right? So what is the projection and all? So I will go through like these things, but with a different style, maybe. Okay, so what we can do is it's kind of a discussion thing we'll do, right? So today's session. So maybe you can answer the questions in between. Maybe I'll be asking you the things, and I will also write along with that. Fine. So I hope that's fine for all of you. Let me know where like in which concept you are feeling difficulties. That way it will be better for me also to traverse through all of these things, right? Okay.
Yes, sir.
Yeah. So all of you, are you able to see the screen?
Yes, sir.
Okay.
Yes.
Yes, sir.
Okay. Nice. So basic. So maybe I'll just show you the. I think this is your first p- um, lecture PPTs, right? So this is four fundamentals of spaces, right? And how to solve all of this. Then we have orthogonal vectors and on and subspaces and projections and the least square, right? So I'll go through this one by one, but we'll try to visualize all of these things, right? That is more important to understand it better. Most of the things I think you guys have learned in maths too, but let us start. So first of all, for before understanding what are the four fundamentals of spaces, we'll try to understand what is vector space, right? Fine. First
Yes,
of
sir.
all, let tell me what is vector. So suppose you have a u as a vector, and one, two, three. This is a vector, right? This is a way we are writing a vector. So what is this vector?
It's a point in any n-dimensional space.
Sorry,
A point in any n-dimensional space.
it is an
It's
n
a
dimensional
point in a
point. Okay,
n-dimensional space.
subspace. Okay, space, right? So can I say that u belongs to R3, right? Maybe I can just say that this is belonging to R3. Okay. We'll talk about this. What is R3 and all. But for understanding purposes, you can say that this is so how many dimensions it is having? Three, right? Uh, Suppose you have another vector like this, 1, 2, and 0, or maybe yeah. So what is the dimensions of this vector v? V belongs to
R3.
R3,
R3.
right? Okay, and suppose this is another vector w, which is 1, 2. Uh, this w vector is in which dimensions,
R2.
R2.
right? So u and v are same or u and v are different? What is the difference between this vector u and the vector v?
Their coordinates are different.
Coordinates are different or same? You just see that with respect to, let's say you have three. Uh, okay, let's say
Both are same
both are same.
No,
no,
there
because
is
zero
different. The space dimension is different.
Correct.
dimension is different.
Yeah.
They are not same.
So
See,
they
they are
cannot.
not same because v is in three-dimensional space, right? And
Yes.
u is in two-dimensional space. So
Mhm.
even the coordinates you can see that like you have x coordinate for x and y coordinates same for v and w, but they are not the same vectors, right? Because v
The
is in
direction is different.
three-dimensional space and
Yeah,
W
yeah,
is
yeah.
in two-dimensional subspace, right? Two-dimensional space. So that is the difference between these two, and that's why this is very important, right? When I'm writing this, R3 means that point, right? That vector is in three-dimensional subspace, right? Or three-dimensional space, and W is in two-dimensional space is a different thing. So when I wanted to show this V in this three-dimensional space, how will I show that? Where this vector will belong? Maybe here. Suppose one
In the
and
in
suppose two,
space
right? Somewhere here.
XY
Maybe
in XY plane.
right. Yeah, it is in XY plane, but this vector is in three-dimensional space, right?
Yeah.
Okay. I hope this is understandable, right? Okay.
Sir, it
Uh,
will become a line no? In 3D if you would say.
this is the line, right? This is a vector. It's not a line actually, right? It's a point here. This is a point, correct? But how we represent any vector with the direction, right? So this is a vector v in this uh, space x. Actually, it is in a plane currently, right? XY plane. Uh,
Yeah.
and it's zero. It is having this z coordinate as 0. Fine. Okay. There is one more thing we discuss is vector space, right? When we call, let's say you have two vectors u. Again, I'll just write 1, 2, 3 maybe, and v as suppose 1, 2, 0. When these two vectors will, uh, we can say that they will contain a space, or when we say that there is a vector space. What are the requirements to have this vector space?
There are certain rules defined
Yeah,
related to vector addition and scalar multiplication, and if they
right.
satisfy,
Yeah. So if we can say that if the linear combinations, right? So if you have all combinations of uh, what is it? U, let's say some Cu plus, let's say dV. If all combinations of this, right, they will form a space, and then we call this as vector space. Is that fine? And here C and D are what? They are some scalars, right? Is that okay?
no,
Yeah.
Yeah.
no, whether we'll call all these linear combinations as this particular vectors as part of a vector space, unless and until all the axioms associated with them are satisfied. This closure under addition, closure under multiplication, all those things are satisfied.
So
No
let's
need
say
to call it a vector space.
you will change this coefficients, right? You will change this C and D, and whatever C and D will be there. Suppose you have, let's say, C and D as 1 1. What does that mean? U plus V, right? So you'll have different values for C and D, and if you take all this different combinations of C and D, maybe plus 1, minus 1, plus 1, 0 0, all right. Uh, if that if that is there, then that all space, entire space, will be called as a vector space of vector v and v, right? And what is one more requirement? That what is another requirement? It should contain 0 0, right? That vector space should contain 0
Zero
0,
zero.
right? So that vector should be there. So that means that C and D must have 0. Uh, uh, is it okay? Any
Sir, could you please explain again?
okay? Okay. So let us say what combinations we can have for these two vectors. Let's say you have these vectors u and v. What let's say if I change the values of C such that all finite values if I take, right, and including 0, and similarly I take the some values for D, right, and if I let's say if I multiply with, okay, maybe I can say that u plus v, right. uh, this be a vector, this addition, this, right, this is vector with C equal to 1 and D equals to 1, right? Is
Yes, sir.
is 0 0 a vector, or maybe in this case it will be 3 zeros, right? So what I'm saying is what I'm saying is all the linear combination. Okay, I'll just write it down again. So C times maybe 1, 2, 3. This is U plus T into 1 to 0, right? If it is if we are getting all these combinations by changing the values of C and D, right? That will form what? A vector space, right? And this should include 0 0 also. Do you get it? Like how it will look like? How this will look like, this vector space?
Sir,
So here maybe you have one,
sum of vectors.
right? So a sum of vectors, but
A plane.
here in this case it will be a plane, right? So that plane containing all the combinations of these two vectors will be called as a vector space.
Okay, sir.
Are you okay? Maybe we have that image here possibly. Okay, in the tutorial, if you just go this, okay, so these two vectors you can see, right? Suppose this 1 4 2. Consider this matrix contains two vectors 1 4 2 and 0 3 3, right? So this column 1 where you are seeing this is one vector and this is another vector. What and the combinations of all these vectors will contain a space. If you see this shaded region, right? This will be a plane, and this plane is called as, like, this plane will form a space, right? We can call it as a vector space. Is that understandable?
Yes, sir.
Maybe I'll try to show you that in some GeoGebra. You can actually go and
Once again, sir,
yeah.
please. The vector space once again define the how in the graph.
You can actually see yourself also, but yeah, okay. Here,
1 4 2 and 0 3 3 are two vectors now, column 1 and column 2.
yeah, consider these two as vectors, two different vectors. Column 1
Yeah.
represents 1 4 2, column 2
Yeah.
is 0 3 3, and all the linear combinations of this, right? If you take all the linear combinations, this will form one space, and that is a column, right? So not column, it's a plane, right? Here in the right hand side, you can see this highlighted portion.
Hmm.
That is your vector space, right?
This is a plane.
This will form a plane, right? Okay, you
Hello. Sir,
yeah,
means all the vectors which are present in that plane are the vector spaces.
they are in vector space of
Okay.
these two vectors, right? U and V. Do you get it?
Sir, I've got a question here.
Yeah.
Can I ask?
Yes, please.
Yeah, like there are two vectors, we are making a
Hmm.
plane. So you can define this vector space to be plane containing both the vectors. Suppose there are three or multiple vectors, then it
Yeah.
will not be a plane, it will be a polytope.
Some other, yeah, that is okay. It need not to be plain,
A
right?
plane.
Always.
It can be
Yeah.
a polytope or whatever shape it takes.
Okay. Yeah. Correct. It doesn't see why we are discussing about plane is because we can visualize it, right?
Correct.
We cannot visualize.
The
Okay. I don't.
polytope or
Yeah.
correct.
Like if you go for higher dimensions, it is very difficult for us to
To
visualize that.
visualize the thing.
Yeah. So maybe we can
Excuse me, sir, can't rows be vectors?
rows. Which rows? No, don't worry about like matrix as of now. We will discuss about matrix. Just think about the vector separately. What is vector? Generally, what do you think about vector?
It has a direction.
Okay, and a magnitude, right? Okay, let's say it is having a magnitude and direction, right? So suppose you have given this 1 2 3. How will you represent it? So okay, maybe in two dimensions we'll try to understand it. So this is your x and y, right? And when I say that there is a vector u, which is suppose, okay, maybe we'll try to see this, correct? You have one vector 1 2. What do you think where it will lie? What's the point here? So
First
basically, it is a
quadrant.
point, right? It is a point,
Yeah,
right?
first
So,
quadrant.
and let's say this is a point. This represents a point here, right? Is that correct?
Point
But,
in
Yes.
the direction.
but this is a
Point.
point. But when I just give it a direction, right? This will become like, or it. I am not giving a direction, but yeah, if we connect the dot by the line which is going through origin, so here it's a origin, right? With, let's say, if I wanted to represent it in the vector format, I'll represent this origin by 0 0. That means its first row the first element here, right? it is it denotes your x coordinate, and the second element denotes my y coordinate, and this vector will be denoted as 1 2, like this, right? And suppose you have another vector v, which is, let's say, -1 and -1, let's say 1. Okay, where this will lie, the second vector?
Left side of
So
another.
minus,
Second quadrant.
right, -1,
Second quadrant.
right, somewhere here, right? So okay, if I'm just saying this as +1, then it will be like this, right? Somewhat like this. Okay, I'm not sure, but yeah, let us say this is another point, right? This is also a point, but we are saying that it is in that direction. Fine. And now I'm just calling it as -1 1. Okay, so now try to see that what are the linear combinations of okay, these are the two vectors we have defined now. Now if I wanted to find out its linear combinations, uh, how this will look like, where all of these linear combinations, what is linear. Okay, first of all, first linear combination, let us try to find out u plus v. What is u plus v? How do you do the vector additions?
If we multiply u with some scalar and v with another scalar.
No, not scalar and all. Here I am saying that what is the scalar here? It's 1 1, right? How you
Yeah,
do where this? Can you just say that this will
1
also be a
minus
vector,
1 and 2
1 minus 1
plus
and
1.
2 plus
right?
1.
How do you do that? Maybe I can do it geometrically, and this will be like how it will
the
look like.
x coordinate. This is the summation of the x coordinates and summation of the y coordinate.
Okay, yeah. So if I can, I don't know, like whether you have studied it before or not, but we can do it this way,
Yes.
and another way is to draw the, like, parallelogram, and whatever the the diagonal is there, that will be your point,
Diagonal.
right? So that is the way, but
Draw a
that,
line parallel to the other
yeah,
vector along the tip of the first vector.
correct. Yeah, so that is also the thing, right? So you have just have to move that one vector on the tip of the second vector, but that can be only possible in 2 dimensions, right? We cannot
Yeah.
do so. We have to find a way to work along with these vectors in higher dimensions, because anyway, when we are going to study about the data, each of this data point we are considering as a vector, right? So that means I should be able to understand the vectors in higher dimensional, but to understand the vectors in higher dimensional, we should know that into the lower dimensions. So here we are just thinking about 2 dimensions, but whatever we are understanding from this uh, discussion, that will also will be applicable to higher dimensions as well. Okay, okay. So first of all, can you tell me what is the addition of these two vectors, 0 and
3.
3?
Sir, are you recording?
Yeah, yeah. It's I am recording also, and it is
Because
available on YouTube. So
no, because I have some network issues and I
yeah,
cannot
yeah,
see the
yeah. It is,
screen.
yeah, it is available.
That is
You can watch it later also. Fine. Okay, where is 0 3 vector now?
In first quadrant.
In
Okay,
y x.
where it is 0 and 3, somewhere here.
Hmm.
So this is what? This is u plus v. That means this is a vector addition, right? So this vector we have got, right? Is that correct? Uh, this is one of the linear combinations, right? When we call the linear combination of two vectors, when we have this kind of format, right? Let's say c, let's say u plus d and dv, and what are c and d here?
Any
Scalars. Scalars.
Any
Scalars.
scalars, right? And they should include 0, as I am saying, right? So okay,
Shouldn't it be on y-axis?
which one?
Yeah, 0
Sorry.
comma
Oh,
3.
yeah, correct, correct.
Yeah, doesn't
Sorry,
make sense.
sorry.
Even if we draw it.
Yeah, sorry.
It will be that rhombus
Yeah,
point
correct.
diagonal.
Yeah.
Sorry. I just missed that. Yeah, right. This should be here, right? Yeah. It should be like I have to make that one, right? Correct. Okay, that's maybe fine. This is one of your combinations. And if you change the values, let's say if I say it's 1 and 2 here, what happens here? So what will be the answer now? What does that mean?
Minus
Yeah,
one
okay.
Minus 1.
Yeah.
Four.
And
Minus 1,
plus
4.
4.
4, right? What this actually represents here, these numbers, what we are doing here?
We are
Scalars.
multiplying
Yeah,
with
when we are
vector.
multiplying, let's say we multiplied this vector by 2, what does that mean? We are stretching that vector, scaling, right? That means we are stretching that vector, or depends on if it is a positive number, that means we are stretching that vector. If it is a negative number, that means we are
shrinking
it, right? Yeah. So now
We are scaling up the magnitude only. Direction is the same.
yeah. So what is the addition of this two? Can you just tell me where this is minus 1 4? So I think minus 1 here and 4 will be somewhere here, right? So okay, is that correct? How we have done? We have just like, because 2 is multiplied with this vector, so the length, so this will be like this, right? This vector will be like this, and I have to add these two, right? That means the thing, this thing. Okay, maybe I think I should be somewhere like this. Okay, but and okay, one more thing I'll do that. Let's say plus 0. What is the answer here? 1 2, right?
1 2.
And if you have 2 here,
2 4.
then it will be on this line,
1 4.
right? If I just say 3, then like this, right? So
Stretch.
we are,
3 6.
and if I say minus 1, the opposite of this will come, right? So are you able to imagine now where the combination will lie, like all the combinations of this? So same thing I can do here, right? I can have C as 0 here, and I have just a minute.
Excuse me.
Yeah, sorry. So what do you think, this, where this span, like all of this, this will span everything, right? Here in the two-dimensional space,
R2.
The first two.
right?
R2.
So the
should cover the entire XY plane.
yes, right? So it will cover, can I just, and it is not limited to what we are seeing, right? It will go to infinite directions, right? So can I say that everything here, right, like this, right, this plane, it will cover by what? All the linear combinations of this, right? Is that correct?
Yes, sir.
So similarly, if I have three-dimensional space, suppose you have, I'm just spending a little bit of time here to visualize all of these things to you. Anyway, it's not needed much for our case, but that will lead you to
No, no.
understand. That is fine, right?
No,
So
yeah, that is fine, sir. We should understand it.
yeah, and then we can just go for the column space and all. That is a later part, but yeah. So let us say you have this x, you have this y, and you have this z, 3 dimensions, and you have two vectors, u as 1 2 0 and v as -1, or let us take 1 3. Okay,
Excuse me, sir.
Yeah.
I have a doubt.
Yes.
How do you represent a vector in when you write it down in R2, R3? Because in the first week the representation was horizontal.
No, I think we have said vectors we are going to consider as a column vectors. I think sir
Yeah.
also said na.
No, in the first week in one of the graded assignment question, it was written in as a
Okay.
horizontal
That is okay.
row.
That is okay. See, it doesn't matter actually. It's a
Okay.
representation
R3
purposes.
R3 can be represented
You can
horizontally
actually
also.
you can write like this, but then we have to mention that okay, what does that mean? This is x coordinate, this is y coordinate, and this is z coordinate.
Okay.
Right? V is
Yes.
equals to. But
So when
generally,
it is represented in horizontal fashion, we call them as coordinates.
yeah.
And otherwise we say that this is a vector. I mean,
Yeah,
actually just
and
the way. Yeah.
yeah, this is a representation purpose. This is not like sometimes people write like this also, right? So, but in our course, we are considering a column vectors, okay, and mostly it is like we can understand it better, right? So by looking at it, like so just understand this part, column vectors. That is okay, right? Now that is fine. It's clear.
Yes, yes,
Okay.
yes.
Now, can you tell me where is this vector u will lie in this space? So if you have, I think you have this side also, this side also, this negative sides. Okay.
XY plane, XY plane.
Where is this?
First
Where should
one,
I first?
u vector will lie in the xy plane.
Okay. So shall
Both will.
I just okay? I'm just removing this. Do you understand, right? This dotted
Yeah, yeah.
things are what?
Yeah,
The
yeah,
extensions of those axes, right?
yeah.
When I just represent this 1 and 2, this will be somewhere here. This point will be here in the xy plane, right?
Yeah.
Okay.
Yes. Yes.
Similarly, where is my 230?
230. So 2 units
2
on
units on
x-axis.
x-axis and 3
3
along
units
this.
on y-axis.
3 on
Somewhere here.
3 on y.
Y-axis. Yes.
Same plane.
Right. Okay. And now you just imagine if I say that CV plus V dV, right? This linear combinations of all these vectors. Where do you think this will lie?
It will lie in xy plane only.
Right. So can I just
On
say
the same
that?
plane.
Can I just say this? It will be like this.
Yes.
But okay, what is this plane? I'll just maybe
This is
not in the z-axis, right? You are able to understand this, right? Maybe my
it's a z equal to 0.
Yeah, correct, sir. We understand.
Right. So this entire it will lie in this xy plane, right? So now can we say that okay? Now I'm just going a little bit ahead. What we are saying this okay? So this linear combinations of these two, right? Cu and dv. Can we call it as a subspace in R3?
Yes.
Yes.
Can we say that?
Yeah.
Yes.
Right. What do you mean by subspace of? So what is the vector space here?
It's a plane.
Entire xyz thing, right? So
Entire
actually
plane.
R3 is a space, and our this Cu plus dv is in R3.
Vector space.
Can I say?
It's a
This is a subspace, right? So this is a subspace, and which denotes what basically a plane, right? Right. The subspace actually it's a plane. So this plane is in R3, right? And it denotes subspace. Is that okay?
So why
now
for the subspace?
Yeah.
Why do we add this by addition? We can say na Cu comma dv.
Cu comma dv. No. We have to take all the combinations, right? Cu comma dv will be the only two vectors, right? And it will not become a plane, right? Then see what will happen to Cu only. It will either this vector will either be here and here.
Okay.
So all the linear combinations over there on the line.
Yeah.
dv is
it will not take the space.
dv is this line. So they will not form a space. They both are separate lines, right? To make them a space, what we have to do? We have to take all the linear combinations of these two vectors.
Yeah, I got it. Combination.
Right?
Yeah.
And then only it will become a plane. Now this is a plane, and this plane is in R3, But and what are the, let's say if I just, okay, I cannot say the dimensions of this two, but yeah, this plane is in R3. So general saying is that this is a subspace in R3. Okay, so
Yeah.
can
Sir,
you tell?
in that,
Yeah.
can we in that case say that like there are going to be three planes, right? Is XY, YZ, and XZ.
No,
So
it
can you
can be having, we can have a lot
three-
of, we can have
No, we
other
can have
planes also,
infinite planes.
infinite planes, right? So there is no, because we can have any combinations, right? See, this is the subspace only formed by two vectors, and where were they? In the xy plane, right? Initially, we can have
Yeah.
one vector here in xyz. Let's say this is the vector 1, 2, 3, and another vector is 1, 2, 0. This will form another plane, right? This may be in a slant direction, right? So the planes can be like this also, right? Something like that, or
Yeah.
at something like this, right? All the linear combinations. So it will have some other vectors, two other vectors, and they will, all the linear combinations will be in that. It will be in that plane, right?
Yeah.
I hope it is fine now.
So
Okay.
that means you can have infinite such subspaces, isn't it?
Yes, definitely. All the planes, but for this to be having subspace, what is the important thing is the plane should go through this 0, 0 vector. This vector.
Yeah.
0, 0, 0. Then we can call it as a subspace. If it is not going, right? Okay, I'll tell you that example also. Suppose you have this x, let's say y and z, and there is a plane which is here. Right? So if this is a plane, right, formed, can I call this as a subspace?
No, because it's not passing through the zero origin.
So the important thing, this to be like the any plane or anything, right? If it is a, when we call it as a subspace, when this has to go through 0. But there are infinite planes
Is
which
it
can go
required
through
to have a 0, 0, 0
Yes.
like origin as 0? We can have the zeros of their own vectors as well.
Yes. Because you see, this CV plus DU, when I say this can be 0, zeros, right? So when they have 0, 0 coefficients, the vectors become 0, 0, 0, and they are actually part of that subspace or part of that plane, right?
Can we understand that this subspace only have, because it passes through the 0, 0 in the in physical meaning, because it can be defined as a unit vector from the 0. Is it so?
Unit vector we cannot say, right? Unit vector is a different phenomena, right? Is this a unit? Okay, is this a unit vector?
No. That is no. I'm not telling that one.
Oh, you are saying that because
why we put the name? Why we put the condition that the plane passing through the 0, 0 origin will call as a subspace?
No.
What is the physical meaning of this? What is the physical meaning of this?
There is no physical meaning and all. Like, okay, I will not say
No,
that.
actually, I think, sir, I think it is like this. I mean, it has to satisfy CV plus DU's condition,
yes, correct.
Which means if C and D takes the value of 0, 0, it should satisfy that, no?
That correct.
Then
so that is what
means
we are defining.
0, 0. Otherwise, it can never go through 0, 0. Right?
So that means we are defining subspace such that this should contain all these linear combinations, and it will contain this definitely, right? That is true. Whatever you're saying is true. So you're just saying that because
that is true. But my question is that we need subspace for our linear approximations or like that, or in linear algebra. So what is the purpose of defining from the 0? Because is it to define that 0, 0 will be counted as a unit? Because origin is including the origin, na? Because origin is required. Is it so, or something else?
No. Whatever you are saying, no. It's not like that. It's subspace is like, we are saying that, okay, when we call it as a subspace, we have given some name. Let's say, right? We are saying that it should
there
be
there is no special meaning. Just we are given a name.
It's like linear combination, because we are saying that it's called to be a subspace when it is a linear combination of
that I got.
Correct,
okay.
Right? Yeah.
Okay, fine. Please proceed, sir.
Yeah. So now let us say Okay, I'll ask you two questions and then we'll move ahead
Sir,
later.
one question here.
Yeah, please. Yeah.
Can we, if we change the origin, say instead of 0, 0, 0, you can have alpha, beta, gamma. So you make a change in the change of origin. So 0, 0, 0 becomes a new origin to a new origin alpha, beta, gamma. So then in that case, we can also have that as a subspace.
No, that will not, because see, again, I'm saying that it should be like it should be a part of this, right? So we are saying that all linear combinations should be there, and when we said all linear combinations, this C and D values should take 0, 0, right? If it is not,
you cannot have change of origin. You cannot have.
No, if you wanted to change of origin, you just have to make it as that new origin. You have to set as 0.
Yeah,
Then
if
only
you
call it as like whatever things are there. Okay, that is not anyway the part.
If you want to shift the origin, then the plane should pass through that origin, alpha, beta, gamma.
Yeah, but then we just have to make sure that this new origin has to be like, because it will become a reference point, right? New reference point in maybe a new coordinate system, but you just have to make it to 0, 0, 0. See, the centering and all is required. Always it is required. All calculations. Why? Because see, we are later on we are dealing with matrices to solve the equations and all these things. Then all of this has to like, we have to assume that all of it should contain origin, right? So okay, that is a different scenario.
Okay.
Can you tell me what are all the subspaces now for R2?
Column space.
So first of all of R2. Another thing,
passing through origin.
Any line.
Any line.
Yeah, through 0, 0, right?
And
that means
origin.
passing through origin. And
origin.
And what else can be? A 0
Origin.
vector.
0 vector.
Yeah, or origin, right? These are the subspaces of, these are the examples of subspaces of R2. Okay, now can you tell me what are the subspaces of R3?
Same addition to R2 as well.
All of R3, right?
All of R3, all of R2, any line passing through origin, 0 vector.
Plane.
All of R2 or all planes?
Any plane.
Any
passing through origin.
Not okay, sorry. Any plane. Okay, plane passing through origin, right? Okay, and any line passing through origin, will that be a subspace?
Yes.
Plane, it should be, right?
0 vector and origin.
Yeah, is that correct? And what else is there? 0 vector.
0 vector.
0 vector, or you can say origin, whatever you want to say. That's fine. Now you understand, right? So what are the subspaces? Now you can just think about like more dimensions also. If you go, it will be like similar kind of structure, right?
The plane passing through origin, na?
Yeah. Okay, I didn't write it. I just said it now.
Any plane through origin. Yeah.
Okay. Now I think vector spaces are understandable. Now shall we go to matrices?
But here the origin is 0, 0, 0, na? 3 dimension is, no?
Yeah, it's okay.
It's okay, na?
Yeah, that's correct.
Understand like that. Okay.
Yeah, it's correct. Yeah, Rohit. Yes. Yeah, tell me. You are raising the hands.
Excuse me, sir.
Yeah, please.
I have one question in the previous section. You said that the plane which is not passing through origin is not in subspace, right? But
no,
geometrically,
we cannot say it as a subspace. That's what I said. It's not in the subspace. It's not the thing.
I was just asking that geometrically, the plane is passing through YZ plane and XZ plane. So can we conclude that it should also pass through XY plane so as to become a subspace?
What we can say is it should go through 0, 0, right? Because let us say you have this plane. When I say that if this plane, XY plane, okay, consider XY plane. Where is the XY plane here?
Z equals to 0.
Somewhere, right? So all the values which are here. So this is a plane, right? Is this passing through Z? Like it is only cutting at 0, right? At the origin. But does it contain any values which are there in Z? No, right?
We have to imagine it to be 0.
Right now. So that is what. So here it's not like it is cutting somewhere into that z-axis, right? But still it is a plane. But this plane is in 3 dimensions of space or 3 dimensional space. That's why we are calling it as a subspace. This plane is like, and what will be your yz plane, where it will be? Will that cut to x-axis anywhere else apart from 0?
No.
No, right? So yeah.
Okay.
Yeah. Okay. So shall we move to the next our things? Is what is matrix then? What do you think? What is matrix?
Collection of numbers in
Or
rows
vectors?
and columns.
Can you talk, like think about it as some vectors?
Yeah.
Yeah, that is correct. Or numbers.
Collection of column vectors or row vectors.
Yeah, column vectors, row vectors, or collection of numbers, right? So matrix is anything different. It's basically we wanted this representation to solve our different purposes, right? So one of the important thing is solving
coefficients of the combinations of the equations also forms a matrix.
Yeah. So, oh, just a minute. Yes.
Okay.
Okay.
Yeah,
So
you can think a matrix like a apartment complex, right? So you have 3 bedrooms on one side, 2 bedrooms on the other side, and each floor is a subspace. So that way you can easily explain.
yeah, sorry, I just didn't hear. So anything? Yeah, can you just tell me again?
Yeah,
Yeah.
you can give this analogy, right? Like matrix is like an apartment complex, and
Okay.
each floor is like a subspace, right? And each column, like for example, 2 bedrooms on one side, 3 bedrooms on the other side, single. So that's like a column feature, right? So that you can give that analogy.
Okay. So yeah, you can explain it better, I guess. You know it, so maybe you can explain it to everyone. So
Yeah, and actually, when you have columns,
Hmm.
the columns are in machine learning. The columns are the most important part of the whole process because it will reflect each feature. So now you can understand when you read about the column, you think, for example, you are going to predict the house price, or you are going to predict anything. The column becomes very important, actually. So if you look at in the machine learning foundation, they will emphasize on each column, and row becomes each data entry into your
yeah, that's correct.
yeah. Go ahead. Sorry, I don't want to
Yeah,
interrupt you.
yeah, no, that's correct. So this is the like it's a combination of vectors, like you can say, or there are okay. We have system of linear equations. I'm assuming that you already have studied. All of you have studied. So basically, a vector like a matrix will look like this, right? So it will have some entries. Suppose I'm saying that A11, A12, A13, so up to A1n. Okay. Then we have A21, A22, A23 up to A2n, and like that. If you have on the, so it is, let's say, AM1, AM2 up to AM1. So basically, and we define the dimensions of this matrix. So generally, what are these dimensions, or what is
M by
this?
M cross N.
This is the M cross N matrix, and here M represents what?
Number of rows.
Here it is number of
Number of
columns, right?
columns.
Maybe I'll just take one simple example that may or may not be, resonant to our machine learning thing, but let us understand through some system of linear equations. So basically, this is a example: 8y plus z equals to 12, and 4y plus z equals to 2. So how should I write it in the matrix format? So there are two ways, right? I can write it like, maybe I can just write it as 1 2 1 3 8 1 and
4 1 4 0 4 1.
0 4 1. But
0 4 1.
but then uh, will that be a good representation to write this in this format, or this is fine? Is a 1 let's say
this is 130, 130, 24, 284, and 111 is fine.
Basically, transpose of the above matrix.
Correct. So this is called as a transpose, right? So what do you mean by transpose? You just
row into column and column into rows.
So basically, transpose is defined like this. I think it is A transpose of
T.
J equals to A, right? So like that, something like that, right? Or maybe AJI, right? So, that element will become the so let's say A11 will become now, or A12 will become A21, right? And that way it is defined as, but that's okay. What is this? This is very important. I'll say XYZ and equals to some 212 2, right? Now this representation is very important. Generally this is AX equals to B, right?
B.
And why is it important? Can I have the same representation? So this will actually, this representation will shows this, right? We can get all these three equations, right? If I represent this matrix in this format and your X in this format and B like that, this will, but if I do the same thing with this, will that give me the same equations?
No,
right? Because yeah, again, I think all of you know that part, so I'm just showing it to you that how we are writing all of these numbers. So what is this 130 represent?
Coefficients of
Coefficients of x's in this case, right? But if I just wanted to represent this as a vector, how this will be then? What will be the coordinates of this in the space? So this
all
is
the x coordinates.
but yeah, how will you let's say if I have x, y, z, how I'm going to represent this now with the vector format?
0 0 3 0 0 0 0.
Where this vector will lie?
1 3 in the xy plane.
Look for an x plane.
No, first of all, that is not even a vector, no, sir.
Huh? Okay, what is it then?
It is a vector.
No, see, see one. We have see. Okay, let me express my doubt. So we have the set of equations here. Then we have represented these equations in the vector form on the right side: 130, 284, 111.
Correct.
And if you do the transpose of that, we got this, the one that is below 121, 381, 041.
Okay.
So now if you take a column, how can that represent a vector? I mean, no. See, any number, if you take a combination of three numbers, it can represent a vector. But in this case, that doesn't truly represent a vector, no, sir. 130.
Okay, which one? Okay, so that's what I'm just saying. No, this is the question to all of you. It's not like I'm just not answering to that. I'm asking you, how should I represent this? Or is this matrix? Okay, what is the difference between matrix and a vector? All of these things you should tell me. That is what I'm saying. I'm not just talking about anything. Is there any difference between the matrix and the vector? Or okay, we can say that okay, all of these vectors. So can I consider 130 as vector in this case, or can I consider 121 as a vector?
130 is a vector.
Okay, let us say if it is
both are vectors.
To me, it is 120.
But it is not representing x, y, z like x plus 2y plus z. It is representing A as a definition. Because the transpose of this and multiplied with x will resolve the is equal to B, is a scalar. That's why we are defining it as a vector. Because
so
we
that,
need
now I know that okay, there are two thoughts here. One thought is maybe you guys are saying that maybe this can be a vector and or it can be vector. So if this is a vector, then what do you think? That x will be 1, 2, and 1, right? So like kind of and when I say 130, this will be a different. So actually the representation of these three vectors, and these 3 vectors will be different, right? That is the idea currently, right? Because they will not be the same thing. That is, I think there is no doubt about that.
Yeah.
Okay?
There is no doubt about it. Yes.
Okay. So let us now. Okay, that is what. Leave that thought there only. Now we'll talk about some things, and then we'll try to understand all of this. Fine. So when I said that A11, A122, A1M, A21, A222, A2M, and here it is A that okay, sorry, I think I just missed it. Yeah, N, right? Just thinking that N columns and M rows of any vector. Okay. Suppose this is my matrix A. The dimensions of this is M cross N, and M represents number of rows and N represents number of columns. So there are, now we have studied all the column space, all the subspaces and all. So
yes,
there are 4 fundamental subspaces. Okay. I think you all have heard about all of that in the lectures. And first is
column space,
we call it as column space of A.
null space.
Null
Okay.
space.
Okay, maybe I'll write out. Okay, then this is null space of A. The third
Row
one
space.
is row space
Row
of A.
Row space.
And another last one is left null space.
Left null.
Left null space.
Left null space.
Okay, left null space. Okay. Left null space is
Null
basically
of
null
A
space of A
transpose.
transpose, right? It's called as this is having only special name, which is called as left null space. But basically it is a null space of A transpose. Okay. That's okay. What is column space of A? It is all combinations of
span of column of A.
Okay, maybe I'll write down okay, span of
columns of A.
Span of okay, maybe can I write like this? C of A is same as
Yes.
a column space of A. And that means what? All combinations of these vectors. Is that okay?
Excuse me, sir.
Yeah.
A column represents an equation, no?
Column represents equation. Which equation?
An equation.
No,
Any equation.
leave this part now. Currently, don't worry about that. Just think about this vector, this A here, this matrix A here.
Okay.
See, this matrix is actually, if I try to tell you, have you, like all of you have studied functions, right?
Yeah.
So, and what do you do in generally in functions? So let's say if I say f of x equal to x square, what does that mean? If I apply
The coefficient of x square is 1.
No, it's not like that, right? So when I say that f
Y,
of x is
y
x square,
is equal to.
There is a range of values for a domain X.
So basically, can I say that, like, if I have like let's say if I have a x some set where we have some values, let's say from 0 to 10, right? Basically, what does it will give to me? Function of x here. If I define function of x as x square, that means for all values of x, right, it will give me all values of x square as x square, right? So that means when I substituted x, right, into that variable, then f of 0 will be equal to 0. If I have f of 1 as, then it will be 1, right? If I have 2, so f of 2 will be what?
4.
What it is doing is we are giving some input to this function, and it is giving me some different output, right, into different maybe domain or different, it is called as a range and domain, right? So okay, all these things aside, but this is basically what it is doing.
It's translating the input into output.
Correct. So basically this is an input and there is some output here, but it does something in between, right? And it will not be the same thing, right? It will have, so x square is might be like it's a, or maybe it is going to give me the cubic equations, all of these things. So this matrix actually does the function of a it actually think of this as a function, right? So if I am apply this matrix over some x, right, it will actually output me something. What is that something? We'll think about later, but basically it is an operator. It's kind of an operator, or it is kind of a function which we are applying on some variables, right? you understand, this is some kind of analogy here. So there is, you can think it as an operator, or you can think it as a function which gives me something else. So initially I'm having some vector 1 2 3. If I apply some matrix A over that, or if I operate this matrix A over that, it will actually give me something else. And what is that something else? Can you just imagine like what it is giving? Basically, maybe it will stretch your vector, maybe it will give me something, it can be, it will give me the mirrors of the vectors, something like that, right? It can change
It
a lot
will
of
have
things.
some operation on the vector.
Yeah, if this matrix A is identity matrix, what would happen? What do you think? What is identity matrix?
Diagonals are 1.
Right, so now this will be like this, right? And if I apply it on what is the output here?
Same,
right?
Same.
So what you can understand, if I apply this kind of matrix over my vector, my like not my, so it is not changing, right? Anything is not changing here. So I'm just getting the same vector, right? Even though it's not elongating or nothing it is doing, right? But okay, if I just, instead of this, what I do here, now what is going to happen here? This matrix
3, 2, 1.
it will invert.
It will be 3 2 1.
Right?
Invert.
Is it invert, or like is it something else?
Something else.
So if you'll try to see this, where is 1 2 3? Somewhere here.
Yeah.
Okay, maybe one is okay. Let me maybe okay. Here is, let's say 1. Here is 2. Somewhere here, right? Maybe this is the vector 1 2 3. Okay, and now what is 3 2 1? Where is 3 2 1?
3 2 1. Below this.
So somewhere like this.
Yes.
Yeah.
Right. So some operation is happened, right? So my initial vector was 1 2 3. Now if I operate this matrix A, right, and by operation of this matrix, what I am getting, so, and is it only this, is this happened only to this vector, or if I take some other vector, it will happen to that also?
Yeah,
It
for
will
any
happen
vector.
to, yes. So there are some special operators. So this is a kind of operator, right? This matrix A is an operator which you operate on some X, and we'll try to get some output there, right? But what are the properties of this matrix A that we are actually trying to learn here? And actually this will be like, this will formulate some subspaces. So when I consider this matrix A as a combination of vectors, right? Combination of different vectors here, and when I'm trying to say that what are the fundamental subspaces, they will be column space of A, null space of A, row space of A, and left null space. Okay. Now, what is this column space of A? Basically, and when I say subspace, we should define this column space of A in which space? It is a subspace in, which dimensions? It is a combination of columns of
RM.
Rn?
RM.
Or RM?
RM.
M. Right? Why?
Because M rows are there.
Right. So okay, M rows are there. Okay, but maybe what we are considering is that we are saying
Length
that
of
all of these
nulls.
are the dimensions, right?
Dimensions of
Right. So basic dimensions, if I try to look at each of the vector, each of the vector is in Rm, and now if I take all the combinations of all these vectors, they will also form a subspace, but in Rm, right? So I hope that is clear. If you consider each of this as a vector here, right, and if I take the linear combinations of all of this, they will be in M dimensions. Is that fine?
Yeah.
Okay, I think that is okay. And okay, now what about, okay, and how to find this column space of A? Basically, if I represent this equation as Ax equals to B, right? Then then okay, that is okay. That is solvability condition. We'll consider that later. But think about it for now. What is null space of A?
Ax equals to 0.
So
Solutions for Ax equal to 0.
yeah. So if you are and in this case, if I am able to represent any vector x such that if I operate this matrix A over this vector x, and if I'm getting x equals to 0, right, then this x will represent what? Null space of A, right? Or no?
How?
Okay. What is the okay?
Yes.
Yes, sir.
Basically, that means, what does that mean actually? But
basically set of all vectors which when get translated to origin of the target.
So all of those such vectors, when I apply a matrix, some matrix over that vectors, and if they are yeah, so you can say that any vector, if you are able to translate it to 0, right, all of that combinations will be what? The null space of A. Basically they are what? Okay, this will actually this will represent the null space, but null space basically will be span of all x's, right?
Yes.
Can I say that? All the if I am able to find out things like this, right? Okay, but now what is the dimensions of this null space of A?
Rn.
Okay, so null space of A is a subspace. It is also a subspace, but it is in Rn, right?
Why Rn actually?
This part I did not understand.
Correct. That is okay. Yeah, that's fine. So let us say you have a matrix A, which is in M cross N, right? Or consider this as a, let's say you're saying that I'm trying to solve some system of linear equations. Fine. I'll take this again, same examples. Let's say x plus 2y plus z equal to 0. I don't know whether this will give me 0 or not, but I'm just saying that
okay, no problem. Just
it's giving me 0, right? And there is another point which is 4y plus z equals to 0. Now if I wanted to represent this into the matrix format, how it will be? 1
3 0 2 at 4 1 1 1.
Then it is 3 0, then 2 8 1 and 0 4 1. Okay, this is okay, but okay. Let us say okay, maybe I'll just drop it for now.
No, actually, shouldn't we write them as columns, each vector? No.
Actually,
because
see,
that's the convention that we are.
I'll tell you
Okay,
that part
sure.
also. So okay, consider only these two equations, and I wanted to represent it in the matrix format, right? So can you tell me what is the dimensions of this matrix? Let us say this is a matrix.
2 by 3.
2 cross 3, right? And now what is your variables here? Or
X, Y, is to
X, Y, Z.
Right? Okay, leave about the right hand side. Can you tell me what is the multiplication of these two matrix and vector? How it will look like?
It will look like
2 cross 1.
So basically this matrix, this vector is 3 cross 1, and if I get if I
2
just
cross 1.
right, so can you just tell me 2 cross 1 means what?
2 by 1.
2 rows, 1 column.
2 rows and 1
2
column.
rows, 1 column.
Right.
Rows and 1 column.
Okay, can you tell me what are these rows?
X plus 2y
plus
plus
z.
z.
X plus 2y plus z.
Right, x plus 2y plus z and
3x plus
3x
8.
3x plus 8y plus z.
And if I say that this is equal to 0 0 0, right, or 0 0 0 0 0 0, right, Now what it is representing? Only this part. That means either this is equal to 0 and this, not either. Yeah, I can say either also, but yeah, okay. So can I just say that by analogy, I am getting these two equations?
Correct.
Correct. So if I wanted to represent these two lines, what I should do? If I just change it, if I reverse it, right? So as we are saying that instead of writing like this, if I write it like another way, what do you say? 1 2 0, right? I don't know why.
1 to 1.
And sorry, 1 to 1 and
381.
381. And if I have x y z equal to, let's say, 0 0 or something, but whether what is the dimensions of this matrix? 3 cross 2.
3 cross 2.
3 cross 2. And what is this? 3 cross 1. Are we able to do the multiplication here?
No, sir.
No, right? So if I have the system of linear equations, the correct way of writing the matrix, or ax plus b format is which one?
As rows.
The first one.
Now you are understanding the part. Is there any confusion now about like how to write this? Now, what if I wanted to consider the vectors in this thing? Which are the vectors now? 3
1,
vectors
2,
will be
1.
there, or 2 vectors will be there?
3, 2, 2.
3.
Sir,
See,
what is the question?
What is the question?
Okay, what are the vectors here? In if I am just considering the matrix A,
Three vectors are there. 3 column vectors are there.
that are you able to? So see, that is what I'm saying. This system of linear equations is different from the matrix representation of that, right? If you're getting my point,
Here there'll be just two vectors, no?
no, you are considering this as a vector, right? Now,
Yeah. If you're considering it as a system of linear equations, then.
But if I'm just looking at the matrix A, what are the vectors? If I'm representing this matrix A, actually I'm representing
Column vectors.
if I'm
Then you're representing as a.
Yeah, but
Go ahead.
so now you understand, right? So you don't get confused into this. Don't get confused into the system of linear
Sir,
equations.
what you mean to say that we have represented the column vectors for the convenience of our calculation because we know how to calculate the matrices. Is it so?
What I'm trying to say is okay. I don't know why this.
Because it is convenient to represent as a column the coefficients of x and y z as a column.
We need to actually represent my system of linear equations in a matrix format, and if I wanted to do that, I should do in this way only. There is no another way.
One thing I've just got confused over here. If you are just transposing the A matrix, you could also transpose X. Then also you will be getting the same result.
Yes. That is possible.
Yeah, exactly.
There is no problem in that. I'm not saying that there is a problem, right?
That will be left null space. It already exists.
So that is the left null space, right? So left null space is nothing like we are doing it differently. What we are doing is we are just transposing to A, and now if I transpose it to A, what will have now? If what is the transpose of A here? 1
it will be 1
3 2 1
2 8
8 1. But now what
XYZ
how many let's say here it will be let's x prime y prime, right? Something like that. Okay, will that be 3 or here it will be 2? 2, right? It cannot be 3. If I am having 3, I'm not able to do but when I'm trying to find, correct, so if I'm trying to find out the solution for this, right, this will be what? This vector x prime y prime, this represents my null space of A transpose. And what is this? Is a null space of
A.
Right? So now you can see that null space of A is basically in which dimensions?
Null space of A transpose.
R3. Or it is a subspace in R3, right? And null space of A transpose is a subspace in
R2.
Subspace in R2. And now you can understand is how I'm defining my null like subspace in which dimensions, it basically depends on number of columns, right? For null space of A. And for null space of A transpose, again, it is a number of columns, but here the number of columns are
2.
Rows.
Right. Now, if you can answer me to this question, and okay, what will be the row space of A basically? Row space of A will be all combinations of
span of A rows.
Or okay, in terms of span, if I just wanted to say, it is a columns of A transpose.
A transpose.
Is that okay? Or
Sir,
all combinations.
Yeah. So this is
Sir.
Yeah.
Sir, the confusion still remains. I mean,
Okay.
see, we know when we can do the matrix multiplication. That we know very clear. Everybody knows.
Yeah.
But the problem is if A matrix A 1 2 1 3 8 1 is given in isolation of anything. I don't have equations. I don't have anything. All I'm saying is I have a matrix 1 2 1 3 8 1.
Okay.
Now,
and how you are representing the as a vector? You are saying, right? That is your confusion, right?
And now what is my vector? I mean, in absence, if I have the equations, I know. I mean, I can figure out.
Matrix is not a vector actually.
Sorry.
Matrix is not a vector. It is just an operator.
It's an operator.
No, yeah, it's an operator. But my columns are representing the vector, or my rows are representing the vector. I should know, no?
Okay, so I think I should. Okay.
You are taking the coefficients actually, na? You're not taking it with the direction. So you're only taking the coefficients. So this is not a like.
The matrix A is defined as the coefficient of the variables of the system of linear equations.
No, perfect. Then how do I know whether it is my equation set is 3? I mean, no, the 3 dimension or 2 dimension depends on how I am representing this, or how I have written this.
Number of columns define the dimensions.
Sir, I know all that,
No,
sir.
no, okay.
The point is, we are saying one way, we are saying that we will represent, columns represent the vector, right? On the other hand, here we are actually truly row represents the vector in the matrix A, correct? I mean, 1 to 1, I know they are the what do you call, the coefficients of XYZ, but I mean, we were saying that actually a column represents the quotients of a given vector. That was the convention, right?
No.
Okay. No, I got it.
Not a given vector. The column defines the coefficient of system of vectors. Coefficient of systems of one dimension, not the whole vector. It is a different vector. What you are telling is a different vector. X, Y, Z coefficient different vector, but taking the coefficients of all the X variable or all the Y variable is a different vector. This vector we are studying to solve the linear equations because it has already been used in our mathematics also. Because matrix is a tool, it is an operator. Just like that, multiplication is the summation only. If you do 100 times, this is 100 into that. So that's why we are doing the same thing. What I understand is that.
Yeah, right.
Okay. Let's hear from him.
Yeah, correct. So that is the correct. Whatever he is saying is correct. It's an operator here, right? We are not consider. So when I'm just saying that, if you wanted to see that 1 3, right, that doesn't represent any point in any space, correct? Like a separate. If I cannot represent this 3 things as a 3 points in the space, right?
What I can't represent, sir?
So you let's say 1 3. Let's say if I wanted to represent this 1 2 1 3, right? Where is that 1 3? If you say that, I'll say that somewhere here, right?
Correct.
Suppose if X Y Z and that.
Correct.
But this is not a correct thing here. When I say if I'm representing this vector, this is not a vector. 1 3 is like in total, if I see, these are not 3 different points, okay? Because this is not a vector representation. When I'm saying that this is a matrix representation, means we are considering okay, you can think of these coefficients here, let's say. So you have this 1 3, right? If what is the coefficient of X here? 1 3. So if I'm writing 1 3, what does it represent here? Nothing, right? like isolate. Can you say that this is a x? This is a, if I say that if this is a point in 3 dimensions or 2 dimensions, let's say, is this a x coordinate or and this is a y coordinate? Is that like that?
No, I
No,
mean
right?
it should, no. Actually, when we say that my column represents a vector, that's what it is. But
no, for our calculation purpose, or maybe if I wanted to say that if I wanted to do some multiplication, if I wanted to do something, uh, if I wanted to solve this, right, system of linear equation, if I wanted to find what are the values of x, y, z here, right, in this case, when I'm solving system of linear equations, what is my goal? To find out the values of x, y, z such that uh, these two equations get satisfied, right?
correct.
Now there are two ways to solve this. What I can do, I can just first thing is maybe I'll multiply with 3 here and then I'll subtract, right? So instead of doing that, right, explicitly writing all of this equation, what I'm doing it, I'm just representing these two equations in the like above format, like ax equals to b format.
Correct.
Fine.
Yeah,
but this 1 3 is not representing any vector.
Correct.
In this case, okay,
Correct.
or 2 8 is not, or even 1 to 1 is not. I'm not saying that it is representing as a vector currently.
Why, sir? I didn't, that I
Why this is a vector? Can you tell me? Let's say 1
no,
to
because
1.
that is the equation from where you have derived this 1 to
Okay.
1. No?
So okay, so okay, just a minute. Yeah, sorry, this is very correct. So if you are saying that if this is your, like, how you're trying to view, right, that is your, like, you can view in any formats, so that is okay. So let us say if I have 1 to 1 here, right? So we can do that also. So 1 to 1, 3 8 1 will be somewhere here, right? I don't know where it is.
Okay, it's
somewhere here, like,
yeah.
There are two vectors. Suppose there are
Correct.
these two vector, 1 to 1 something,
3
or
8
maybe
1.
I don't know, whatever the vectors are there. Let's say this is u and v.
Correct.
How will you solve this to get this 0 0?
So that's, I mean, see, sir, I know
Correct.
how to write the matrix A. I
Yeah,
know
yeah.
how to write the
Yeah.
I mean, x, y, z, the variables, and I know what to equate it to.
So
I solve it. My only confusion is one side we are saying that we represent a column represents a vector. In this case, u, let's say the case of 1 to 1 is the u, then ideally, as per that convention, the column should have 1 to 1. But if we have 1 to 1 as the column representing that vector, then I understand the problem that I will not be able to multiply with the 3 xyz variables. Right?
Okay.
And so we take the A transpose and multiply.
Okay, I think I don't know. Maybe I have given you the wrong idea about it or something. I don't know. But when I say column represents, or if I'm representing any vector like this as a column representation of vector, right? This is what I am trying to say. I'm just saying that in this course we are representing the vector by a column. I'm not representing the vector by like this. Though I can do that also, right? But when I say that matrix in the matrix format, this you can consider them, or you can treat them as vectors, right? But they may not be the vectors like this. So here what we are saying, right, we can think of that as a collection of vectors. Suppose there are, let's say, these are vector a u v w, or they may not be equal to like the same as that of this. We are using this as a tool, like matrix as a tool, or right, to solve our problems, right, or to solve for some values. So we can consider them as a vectors or not, but okay, I don't know how to like say that.
Sir, no problem. I actually you proceed. I think
Yeah,
probably I am
correct.
disturbing too
Maybe
much.
we can discuss it maybe later, right?
Yeah.
So
I will find out if anybody in the class understands this concept. I'll talk to them
Okay.
offline.
Okay. I think we should stop this now. Yeah.
Sir, I have one
So what
question.
happens is when we use
When we are doing this
null space or column space or row space. What I was trying to understand is, um, uh, do
Can you just
we?
there is some noise in your side?
Yes, yes. I just switched
Okay,
it on.
yeah.
Actually, there is this mentor session also going on. There is a clash between two sessions,
Okay.
but they cannot change the timings, so
Yeah.
it's okay. What I was trying to say is, what is the use of these null space, and means how do we apply it to real life situations?
Yeah, you will learn it eventually. Like, that's what I'm saying. It's like too early currently for you to you know use that. So just
No.
yeah, I understand your
Application.
point. How we can use it, right? So I understand your point. Uh, okay, so basically, whatever in machine learning context, if you wanted to understand it, right? So
Yeah.
every data point, whichever you are having. So how is your data actually? So let us say your data can be in a textual format, or maybe let's say in numbers, right? So basic, if you consider that house price prediction, I think all of us know that data set. How does it look like?
Yes, the house
Yeah,
prices,
what
depending
how
on
this,
the
so price will be
whether
your,
it is
yeah,
close to a school, whether it is close to
yeah,
a
so
train
area and
station
distance,
area,
right?
and
Okay,
number of rooms in the house,
correct.
or the area of the plot,
Yeah,
and a lot of attributes are there to the
right.
house.
So suppose
So,
I'm just taking these two the two things, right? Area, distance, and price now, right?
hmm,
So and you have, let's say, so we have number of examples, right? So this is say the
hmm,
first example. There is another example like this, let's say 300, 2 and 4, right? Like maybe it's in the price, it is, let's say, in lakhs rupees.
hmm,
Doesn't matter for okay,
hmm,
maybe 100,
hmm,
100, but 0.5, and suppose it is 6 lakhs,
7,
6 7
6,
whatever, huh? These are
7.
the examples, right? So
Hmm,
now if I wanted, what is the thing which I wanted here, like to predict the price, right?
hmm.
For
Yeah.
the new data point, not for this.
Yes.
This is
Hmm,
already way I'm having. I have to learn
hmm.
something from this data and try to
Yes.
predict for the, if I have something else, how can I
Else. Hmm.
let us say, by learning all of this data,
You
someone
have
student,
something for area 250,
yeah, let's say
distances one
250,
and a
and
half, or
okay, and what is the price? That
what
is
is the
my, yeah,
price?
that is a test
Yes.
point, and that other
Test.
things are the
Hmm.
data point.
Hmm.
But then how to solve this? Like machine learning means what?
The
If
machine has to predict the
correct, it's not
value.
human based, right? Human based is there,
Hmm.
there is some human, and
Hmm.
the broker will be there, he'll tell you some price.
Hmm.
But no, we wanted to learn it through machine, right? Machine learning. So
Hmm.
but how does machine learns? Through numbers, right?
For numbers.
Right, so because machine is what? Computer is like, it deals with only numbers, right? And it will do
Yeah.
some numbers, and
Hmm.
there are various ways, which is calculus,
Hmm.
algebra, and algebra's part is linear algebra, let us say, or maybe it's a linear algebra. So linear algebra is what? Okay, can I say that I can say this as x, y, or maybe x1, x2, two variables, and y as a label here. How does I should represent this, uh, right? So that I can just find out the y. So can this be seen uh, by linear algebra perspective? What does that mean? Can I create
We'll
a
have to
matrix,
create the matrix
right,
and
and
then
try
try
to
to
solve for
solve
it,
it.
right?
Yes.
So okay, and suppose there is another variable here, which is, suppose, let us say, area square, fine, which is, or maybe let us say distance square. Another variable is given to me. I'm just giving you the example, it may not be true, but let us say you have some variable which is, let's say, 2,
Distance from school, say,
yeah,
or distance
yeah,
from
this same distance,
train
I'm just taking it
station
a
or
square.
something.
Yeah, I'm taking a square of
Hmm.
it. Okay,
Hmm.
maybe 0.25 and whatever. So this is another variable given to me, x3. So now if I wanted to, okay, maybe I can just make it as x1, x2 and x3. If I leave now we don't care about this. If I wanted to make this in a matrix format, how it will be? How will you represent the feature 1? Maybe 1
201
4.25.
142.25.
Right. I'm just
300 100.
Right. Okay.
Hmm.
1 5. You can actually say to them as XYZ also.
Yes,
Right?
yes.
But I'm just saying that x1, x2, x3 because this y is
Hmm.
there, which I'm interested in predicting. So these are, let's say, x1, x2, x3. But and let us say you have many things here, right? So what are the dimensions of this vector x1? These things, right? Correct.
Yes.
This will be a vector here, right? This will be some vector,
Yeah.
and this is another vector, something like that. But now you can understand this. This x1, actually x1, is there any difference between x1 and x3 here?
No.
Is it the same thing, right?
It's same.
Okay,
It is
so
just a square. So one of them is independent and one is dependent.
okay, so in this case, what is the column space of A? It's a span of maybe I can say x2, x3 or x1,
x2,
x3.
x1, x3 or
x1,
x2,
x2. Sorry, x1, x2 or
x1, x2 or x,
yeah, something like that. Let's say
x1, x2 or x2, x3.
Yeah, right. Okay, I'm just taking that square distance, but let us say I took it like 2 times distance or something. That was my variable. Now you just understand that why now is this important now for my understanding the column space of A? I should
Yes.
consider only these two vectors, and I shouldn't consider that the other vector, right?
x1.
Correct.
Yes.
So and then will this and what will be rank of this matrix?
A span is the independent vectors, no?
Yeah, span of the independent vectors. Now, since I am
No,
having
rank is 2.
rank is 2, and then what will be my null
And
space of A here?
null will be 1. Nullity will be 1.
Nullity will be 1,
1.
right? So when I am having null space as 1, in that case, solving this system of or solving this matrix by using the machines, will that be difficult or will that be easy? If I am not having the full rank, if I am trying to solve these equations, right? Let us say if I'm having some equations. Actually, I wanted to find out what are the linear combinations of this to predict the price y. But you just see that all of this will depend. If I am having a matrix, right? If I am representing my data through a matrix, that means all the properties of matrix, right? To calculate all the other things, I should know. And to understand all this, right, I should know the basics of linear algebra, and that's why I need all of this information about what is column space of A, what is null space of A, what are these properties, and then later on we'll build on that to understand it data. Right?
Yes.
So to understand the data and understand the algorithms related to that data, I should know all of these things. Correct?
Sir,
Yeah.
One
yeah.
maybe stupid question, but how you are saying x1 and x3 are one and same?
Interrelated.
Yeah, one on the same is like, okay, let's say this is
We have
x1 is, let's say,
taken either
2 times distance. What is the values
or
here?
2 times distance or square of the
2 times distance is 2, 2
2.
to the 4 and
No,
1.
2.
Right?
Correct, but then how?
No,
It's
it
not
will be 4.
two
No,
users.
2 times distance will be 2, 4 and
Okay, fine.
0.5.
Right? Now,
Then fine.
1, 1. 2, 4
right
and 1.
now, yeah, that's what I took, like 2 times distance. So now
Uh-huh.
it's a linear combination, right? Here, or what
Linear
what I
combination of
Now fine.
x3.
Earlier values were
yeah,
not
yeah,
linear
yeah,
combination of x.
that's why I changed it later on. I just like
So now
through
x2 and x3 are independent and x1 is dependent on x3.
no, here x1 and x3 are dependent, right? Because it's like 2 and 1 actually is like 2 times this vector, right?
Means
x2
we
is
have 2
independent, right?
independent vectors.
Yeah, 2 independent vectors
One
in
is
this matrix.
two
Correct.
independent and one
Yeah.
nullity.
So now you see all of this is very important because when you are feeding this data to your machine, it's not like we are actually learning for 2 by 3 cross 3 matrix or 2 cross 3 or 4 cross 4, right? They are very easy matrix for our calculations, right? But when you feed the data to the machine, or the computer, how vast data that is, right? It's a very vast data, right? And that means the computational power also will require that much. And if you don't understand the notions of this column space, rank,
here
nullity,
actually we have taken only 3 variables, but there are multiple variables.
Correct, multiple variables, multiple
find the
dimensions,
price,
right? And multiple dimensions also,
multiple
right?
dimensions are there for finding the price.
Right. So in that case, if I know that what is the column, what do you mean by column space of A, what I'll do is, if I understand this, right, what is the rank or something, then finding out the predictions, what I'll do, I can just drop one column, right?
Yeah.
I'll just take other two and try to find it out. Now the competition will become easier, right? This is very layman. Whatever I'm saying is very layman terms, right? I'm not actually dealing with all of this, but since it is a very early stage of ours, we have to understand the basics of linear algebra, right? So now I think I'll just summarize it. We have 4 subspaces, fundamental subspaces. One is and okay, for if I'm defining
column
a matrix
space,
Mn, we have null column space of A, which is a linear combinations of all columns of A when we try to solve this equation. Okay, that is again I'm trying to say. And when this is solvable, when this B vector is in column space of A. Okay, that I'll tell you about. But yeah, this is a linear combinations of columns of A, right? And it's a subspace in R M. Null space of A. When how to find out null space of A? If I just solve this equation x equals to 0, then this x will represent what? It will represent my null space of A. Fine.
Null space of A.
And what are the dimensions of it? Or it is a subspace in. I'm just saying that a subspace.
R of n.
Yes. Subspace.
R of R minus.
No, R. Okay, we'll think about here.
R
so
of
if I wanted, so this is a subspace, right? And what are the dimensions of this? Or it is in R2, right? And that is actually equals to number of columns, you see. Okay, so when it is a number of columns, that means it's in 2 dimensions, right? If I just look this vector as like this, or this vector as okay, that will again create a confusion, but okay, try to understand that this null space is in 2 dimensions. You have if you just see that this matrix is 2 cross 3 matrix, its null space is in R3, okay, or it's a subspace in R3. Okay, similarly, what about column space of A transpose? This is a linear combination of what? All the rows of A, or I can say that columns of A. This is same as that linear combination. Am I audible?
Yes.
Yeah. Linear combinations of rows of A. Is that correct? Rows of A, columns of A, or rows of A transpose. Oh, sorry. I think I'm just writing it. A transpose and A. Is that okay?
Yes.
This same, right? This is equivalent. And how to solve this? For how to find out the column space of A transpose? By solving this equation, maybe to B, right? Or now it's not required actually. You just need the combinations of A transpose. So linear combinations of columns of A transpose, and this is a subspace in Rn or Rm. Rn, right? Is that okay?
It's a transpose, right? So
yeah, it's Rn. Okay. And what is a left null space, or basically this is called as a left null space, and what are the? It's a subspace in Rm.
Rm.
Okay. And how to find the left null space? A transpose x prime equal to 0, right? And this will represent my
Y.
Okay, y. Okay, we'll do that. Y. That's okay. Done. This is your null space of A transpose. There is one important theorem which is called as rank nullity theorem. So, what is the rank nullity theorem? It says rank
plus nullity is equal to number of columns.
Number of columns. Number of columns. And rank represents what?
Number of pivot column.
Or dimensions.
Pivots.
Yeah, or dimensions of
A.
No.
Column of
No,
A.
no, no.
Column space, right? Column space.
Column space of A.
Column space of A, right? And here it's a dimensions of
Null space of A.
Null space of A. Fine. This is not dimensions of A. It is a dimensions of column space of A, right? Or
This rank of A.
Dimensions of column space of A, or I think okay. This will be like odd, right? This will okay. This will seems okay, but okay. But rank you can define as number of columns minus dimensions of null space of A, and this dimensions of null space of A is called as nullity. That is clear. That there is no confusion here. Okay. I think this all of you all know, right? I should not worry about that. Maybe is that correct?
Yes, sir.
Okay. So
just one question.
Rank
plus nullity will be number of columns, or it should be number of. It can be also number of rows, or it will be only number of columns.
This rank nullity theorem, it is for this rank plus nullity equals to number of columns. Okay.
In case of rectangular matrix, will that be okay?
That also be rank plus nullity equals to number of columns. If you wanted to change it, right, then that will be your row rank, right?
Yes.
Then row rank plus left null space, right, or nullity for that, and then number of rows. But basically, this is for the this will be defined. That is applicable there also, but then you just have to again. It is the same thing, right? It is not a different thing. Because rank plus nullity equals to number of columns. When I'm saying it is for matrix A. If you just go for the transpose, then that rank will also be for the transpose of the matrix, right? Okay. I should not. Maybe I just tell you about.
Can we understand this? Rank is the independent column matrices, and nullity is the independent column matrices. Both summation is that the number of total columns. Is it so?
First thing is what you said. Rank is what?
Rank is the independent column matrix.
Number of independent columns. Okay.
Number of independent columns, and nullity is the independent columns.
Not columns. Okay. Okay. Fine. Okay.
Just to understand. Just to understand. Not mathematically.
Nullity is what you are saying.
Dependent columns.
No, not like that. Or will it be same? Okay, I think it is coming as same. Okay, fine.
It is coming the same, no?
Okay.
If it is dependent.
But this should not be say, right? But okay, but for your if you wanted to remember that way, it's fine. But you should understand, right? What is it? Basically, you know, right? When I solve this Ax equals to b, then or x equals to 0, then this x will represent my null space of A, right? That is my understanding. Now you just however you want to remember, you just remember. Okay. Do you know what is the solvability conditions? What do you mean by how to solve the matrix or solve the system of linear equations? When we say that Ax equals to b is solvable. And what
determinant must not be 0.
Okay. One thing is determinant of matrix A should not be equal to 0. Okay. What does that other meaning of it? Is there this determinant? You know, connected to the column space of A or something like that. Okay, just give me a minute. I'm just coming back.
Is anybody 100% clear on that how to treat that vector and stuff like that, friends? And anybody willing to help me?
I guess it depends on the context of the question. So if it's like a linear expression question, then you use it as
No. See, if the equations are given, I know how to solve it. But you understand I hope you understand the reason for confusion. If we don't get a chance here, is there a way to connect offline to get your help, get some help from you?
I think you can post it on discourse.
Okay, thank you.
Actually, your confusion is not with that. On discourse, it cannot be resolved. It is a matter of discussion.
That's the problem. That is the problem. See, a concept can only be taught. It cannot be actually discussed in the textual form. Actually, that's the problem.
When you go to the more than 3 dimension, it is not a tangible thing. It is an intangible thing. And this data science is always working on the intangible things, just like probability. You go to the casino, you have must learned in the, I think, math 2 also, math 2 or statistics perhaps, in the probability, when the n goes to more than some number, more than capital N, then the probability becomes always in the favor of the casino owner. That is a mathematical fact. But in practice, we cannot understand going to the casino is whether we are winning or losing, because the person will lose, but the casino person will always win, because the footfall is more than 2 lakh people. If you go to the 4 people, the casino may be closed. This is the mathematical thing, which it cannot be tangibly understood. But what you are discussing, that is confusion. Because normally we represent x, y, z as a vector, what you will learn in the mathematics.
Correct.
And the coefficients are, but this is another vector we are dealing with. That is not the same vector. You just separate both of them. This is the tool, mathematical tool, matrix we are using as a mathematical tool to operate on some system of linear equation. That is one part of that only. Because this is having the multi-dimension. When you go to the 100 dimensions, then it is not a system equation to solve. It is a just mathematical tool to predict something that is not also sure.
Okay, so I don't know what is the discussion going on.
No, sir. Okay, sorry.
Okay.
Sorry, sir.
It's okay. No.
Sir.
I was not there.
We are just trying to discuss about the same point that I'm
not
clear. I'm trying to get their help.
Okay.
You can proceed.
No. See, the thing is, you can actually, so looking at a way, right? I understand what is your issue. I understand actually. So the thing is, you are stuck with that part, like how to represent this x plus 2y or something, right? Actually, you can consider these two vectors in a different way.
No, sir.
Try to solve
given
this.
equations, I know how to write them. I know how to solve them.
Yeah.
I know end to end. My only problem is in Maths 2 also, I was having the same problem.
Okay.
I mean, if a set of vectors equations are given, then when we were representing in the matrix form, we were writing them as columns and stuff like that.
Yeah.
So some places, I remember seeing those each equation being represented as a column. Sometimes I see each equation being represented as a row.
Yeah. So it's actually its answer is in your words. So you are saying that you are representing it something, right? So how to represent anything, it's in the hand of yours, like ours, right? Like how we wanted to represent that thing. So I wanted to representing in any way, but what is the final thing? I need to find out the answer or solution to that, right? You can actually represent that same vector in a column format, like as like coefficients of x in a column format, or you can actually represent them in a row format. Okay, and you create a matrix. For example, if I'm saying that x plus 2y plus z equal to 0 and 2x plus 3y plus z equals to 0, if you represent it is like this: 1 2 2 3 1 1 and then x y z, and try to solve this, right? And
Correct.
think of these three as vectors and try to find out certain combination of that. If I try to find out the certain combination and that gives me 0,
Correct.
then this is fine. Or what you can do is you just try to find out or make them as like this, right? And now you have to solve for some x prime y prime, right? And now you try to find out the combinations of these two, and then you say that this xy is the, so this, I have you learned about LPP, that linear like programming, some, I don't know the full form, it I just forgot it, but there in that, right, there is a problem of duality, if you know or heard somewhere the
No,
dual
sir.
problem.
No
This
idea.
equation actually I can represent in a different format. You'll know that it's
Okay.
there in the optimization process, right? This
Okay,
x
no.
plus 2y plus z equals to 0, actually I can change the variable names and I try to write in a different format, but then
So how do
this,
we solve? How do we solve three variable equation with two equations?
yeah, so that means there is a redundancy, right? So this is not possible, right,
Yes.
here. Okay,
Hmm.
and that's why actually it comes, right, that solvability, so the projection and all. Okay, let me go through it. First of all, representation is the thing, is like how you wanted to represent, but final thing is you should be able to come up to the answer. That is what
You can understand like this also, a left to right and right to left. People write, na, some people write from right to left, some people write left to left, but everybody is fine with that. If he is habituated with that, then he can do that.
Okay, so that's the
Let us,
later part. Maybe we can just discuss it later on. We'll
then
try
let
to
us
finish it up.
discuss.
Okay.
Yeah, yeah, yeah.
So when I say this ax equals to b is solvable, so it is solvable when this vector b, right? I'm considering this as a vector b. B is some or it is called as a b is in column space of A. Generally, it is said that to be b is in column space of A. What does that mean? What is the column space of A? It's a linear combinations of all the vectors, right? So consider A as a vector. Let's say A1, A2, and let's say A3. Okay, there these three vectors are there. Now, what does that mean? B is in the column space of A. What is the column space of A here? The span of vectors, right? A1, A2, A3, right? So if B is equal to A1, can this equation be solved?
Yes.
Yes. If B is A2, can
Yes.
this equation be solved? If B is A3, can this equation be solved?
Yes.
Can A1 plus 2A2, can this equation will be solved?
Yes.
And what I'm trying to say is, if it is like that, let us say some constants. So constants, I'll say that W1 A1, let's say W2 A2 plus W3 A3. So if B is a certain combinations of this, right, or maybe any combination of this, then the system of linear equation is solvable. What does that mean now? What is this actually?
Linear combination.
Of yes, right. So that means
The
all the vectors
columns.
are actually in that space, right? Let us say if A was a two-dimensional vector, then I should have written like this, right? And what does this represent? Does this represent a plane? W1 A1 and W2 A2, where W1 and W2 are some scalars.
Yeah, it is a plane.
Right. So what I'm trying to say is, if B is a vector which is in that plane, right, then this system of linear equation is solvable. Is that fine?
Yeah, geometrically, it is
Geometrically, I'm
fine.
just saying.
Geometrically, it is correct.
And how will you solve this matrix then?
If the B vector lies in the plane of W1 A1 and W2 A2, then it is solvable.
It is solvable, right?
Yeah.
Basically. And now we'll try to find out its alternative meanings. What does that mean? The rank should be, or this matrix A should be a full rank matrix. Okay, should be a full rank matrix. What does that mean again?
The column space of A, yeah. It has the dimension of the column space.
So what does that mean? All the
number of pivots equal to number of columns.
Or all the vectors inside that matrix A, they are
linearly independent.
Pardon?
All the vectors of A, or maybe vectors, I'll say that, let's say, now if I'm
are linearly independent.
A1, A2 or some, these things are
independent
linearly
vector.
independent.
Yeah. All right, all should be linearly independent. What does that mean? Determinant of A
should not be 0.
Should not be equal to
non-zero,
right?
invertible.
Right. Again, okay, so all of these things will be clear, or this is okay, right? So yeah, so
no, it is okay.
No. This matrix A is a full rank matrix when all, okay, so no, that is a different description. Sorry, I just did a wrong thing here now. So matrix A is a full rank matrix when I say that when all these combinations are, or all these vectors are linearly independent. In other words, I can say that W1 A1 plus W2 A2 plus W3 A3, like that, should be equal to 0, right? It should be equal to 0. That is the meaning of it. And that other meaning is determinant of A is not equal to 0. How to find and when to say that this Ax equals to B is solvable is when, let's just say, if this is a matrix, then this is called, what do you call this? Called as augmented, right?
Augmented matrix.
Augmented matrix.
Yeah, augmented. Okay, augmented matrix, right? And in this case, this call is solvable when the rank of A should be equal to rank of this, right? Is that correct? Then only it is solvable, right?
Yes.
Okay, we'll try to find out now.
Rank will always be, if it is augmented, then both rank will be same now always.
No, they cannot be, right? They may or
is
may
it
not
possible?
be.
Is it possible?
Yeah, if they are not same, that means B is not a linear combination of.
My question, is it possible the rank augmented matrix has a different rank than the original matrix?
Yes.
Okay.
It should be, right? It can be. Okay, we'll try to solve this. Okay, maybe I'll give you the example. 2x plus 3y equals to 1. We'll solve for only two-dimensional case, okay?
Yeah.
Maybe 4x plus 6y equals to 5. Okay? What is the matrix? What is the ax plus ax equal to b representation of this linear equations?
2, 4, 3, 6.
3, 4, 6. Here it is xy. And what is b?
1, 1, 5.
1, 5. This is a, x equals to b, right?
Yeah.
Okay. Now, what is the augmented matrix here? This is 2, 3, 4, 6. I'll represent this 1, 5. Is that okay?
Yes.
Okay. Now, if I wanted to solve this matrix, augmented matrix, what should I do? First, I have to use the row reduction operations, right, to find out the ranks and all, or to solve this, right? So first will be what? First operation is R2 changes to R2 minus 2 times R1.
2 R1.
And this will become 2, 3. Okay. The same operations I have to do there, right? Okay. So here it is 0, 0. And what is here? 3?
Minus 3.
5 minus 2, 3, right? 5 minus 2 times 1.
Yeah, okay.
Correct.
Okay.
So now, can I do further anything else here? This is a row, not row reduced. So it is a reduced row echelon form, right? Or it's a
REF. It is REF.
It's only REF, right? Okay. Now, what is the rank of A here?
1.
This is A, right? This is A.
Rank of A is 1 and rank of...
So rank of A is equal to 1. Why?
It is unsolvable.
Why it is the rank of 1?
Number of non-zero rows.
Right. So how many number of non-zero rows are there in A?
1.
1. That's why the rank of A is 1. And what is rank of A augmented B? So A augmented B is the entire this matrix.
2.
Okay. And what is the rank of it? Equal to 2. So can you tell me that rank of A is equal to rank of A augmented B here?
Hey, rank of A. Rank of A, the number of rows. Okay, non-zero rows. Okay, 1.
Correct.
Yeah.
And in A augmented B, do you have any non-zero rows for row reduction? So row echelon form. No, right? Is
correct. Got it.
So what does that mean? This system of linear equation is not solvable. When this would have been solvable? When we had, instead of 2, we had 5, we had 2. So is this a perfectly solvable thing? So can we solve this now? Now what is, if I do this operation, what should I get now? Is equals
if
to
the rank is equal, then only it is solvable, right?
Then it is solvable. Now this is solvable. And okay, in other words, like what I am saying is, when I said to that, the meaning of this is like, if B is in column space of A, right? I said this is a solvability condition. What does that mean? Now we try to see it. This B, right? 1, 2. Yeah. Does it belongs to the column space of A? What is the column space of A here? Span of
2030.
2, 4, 4, 3, 6.
3, 6.
Yeah,
right?
yeah.
Is it correct?
Yes, it is. Yes.
So can 1, 2 be linear combinations of any of this? Can I represent 1, 2 as a linear combinations of these two vectors?
Yes.
Yes.
2, 4.
2 times column 1 and
half times 1, 2, 4 plus 0 times
0 times 3, 6.
3, 6. If I, and that should be equal to 1, 2, right? That means B can be represented as a linear combination of columns of A, right? And then only it is possible to, what does that mean is, this 1 and 1, 2, if you think about geometrically, this vector 1, 2 is in the plane of that column space of A, right? Are you able to like connect to that part?
Yeah.
Right.
Connect to that.
So whenever your vector, the B vector, if it is that in that column space of A, that means you will be able to find out the solution, right? So, and now what is the solution? How to find out the solution? That will be your next part, right? Correct. What is the solution to this problem now?
Or alternatively, we can say that we can be able to generate this 1, 2 from these two vectors, right?
Correct. Yeah, that is what, same thing, right? Yeah. If you are able to generate, means what? You are trying to find out some linear combination where you did this, right? That's the same thing, right? Yeah. Okay. I think you are understanding perfect now. The thing is, okay, now just the final part of this, so that I'll just jump to the next part and then we'll finish. Give me like half an hour.
So here we are not interested in the solution, that half and the 0.
Hello?
Something, everyone's gone mute. Hello?
No, perhaps. Sorry is on mute, perhaps.
Am I on mute?
Okay. Yeah, okay.
Fine, right?
Audible.
How to solve this system of linear equations? I will just do R2 changes to R2 minus R1, right? Or 2 times R1.
Yeah. 2 times
Same
R1.
thing I did for augmented. I'm just doing it normal way, like as we do for, I think that is Gaussian elimination technique or something.
Gaussian elimination.
2, 3, 0, 0, x1, x2, or okay, not x1, x2. Here I'm using xy equal to What? 1 0
1.
0, right? Now solve this. What is the solution? 2x plus 3y equal to
1.
1, right?
And 2x plus 3y is equal to 0.
Where is 2x plus 3y equals to?
Oh, no, sorry. Okay, got it.
Are we able to reach to this part? Now,
Yes.
So, and what? Okay, maybe I can do for one more step here, but no, there is no other step. Okay, what should I do now here? So 2x can be written as 1 minus 3y, right? Or x can be written as like this. So we are able to find out the situation where I can have actually that if for some y I can find of x, right? That means we are able to find out these two coefficients x, y such that we can be able to solve this problem, right? There are other ways to find it out. What are the other ways here? If this was the equation 1, this was equation 2, what we have done generally? We do like we subtract 2 times or something, right?
Yeah.
Substitution method.
But in that case, we get the value of x and y.
Yeah, here what is the issue here?
We are not getting the value.
Because these are parallel lines.
These are the parallel lines, right?
And 4x 6y.
Okay. Correct, na?
Rank is 1, same thing.
Right. So
infinite solutions.
We will have like we can have any other values, and we can have like so many values of y, but we'll be able to achieve this, right? This for that is why it is having infinite number of solutions.
Even from the equation we can get for any value of x, you will be getting the y value.
Right. So now we'll conclude it now again. So when I say that rank of A, so this is I'm just denoting row as for rank. Fine. If rank of A equal to rank of A augmented vector is B, if it is, let us say, if my matrix is M cross N, what is the rank here? If M is or N is M is greater than N, in that case, what is the rank?
M.
M, right?
M.
Okay, M, or let us say I wanted that rank, let us say M is less than N, something like that. Okay. In that case,
M is the
that
rank.
N. Okay. I'm just saying that if it is N here, in that case, I will have what? Unique solution.
Unique solution.
When rank of A equal to rank of A B, which is less than maybe N here, right? Correct?
No solution.
I have infinitely many solutions.
Less than N. Yeah.
Right. And when we have no solution, when the rank of A is not equal to say B, in that case we have no solution. Okay. Now we have to worry. Okay, for this we can find it out. And what does this mean actually is how many number of variables you are having, right? You will have that many number of equations to solve that. But okay, that is the part. We don't have to worry about this now because we somehow we are getting solutions to that part. We are not getting the solution to this part. And when I am saying there is no solution, what does that mean? What can we say about B? B is not
in the column space of A.
Right? Okay.
If there is no solution, then B is not in the column
space of A. Fine, right? No, or vice versa. If B is not in the column space of A, that means you will not get a solution. Both the statements are equivalent. That's okay. Okay, but that solution
and geometrically it means that the linear combination of the column space of A will not have the vector B. Is it
correct? Will not have that vector B
geometrically.
Correct. And that is what we are trying to build that geometric understanding now to and okay, but still we need some solutions, right? We need some solutions, right? Otherwise what we will be stuck, right? So we cannot be able to solve those kind of equations. So we may not get the actual solution, we'll get some approximate solution, and the techniques to that is projection. Okay.
Okay.
And that's why we need that projections of why we do the projections is to find out some solution that will not be the actual solution, but it will be approximate solution. What
Some
we are
predictions.
what we are trying to do, I'll just let you know. So first of all, we'll study about what is the projection of a vector. Okay, fine. We'll try to understand it geometrically, and then I'll build that concept to the matrix. Okay, because it will be again the same thing. So let us say you have some vector B here, and there is some vector A. There are two vectors. Okay, I wanted to project that vector B onto vector A. What is the how to do that?
Draw a perpendicular line from point B to line A.
Fine. Okay.
Yeah.
And what does this portion will represent here?
The difference.
This is the projection.
This will be the projection.
Projection vector actually, right?
Yeah,
It's
this is a projection vector. Projection
vector and or okay, vector it will become when I just multiply with A, right?
Yes.
If you understand it properly, this is a projection basically.
Yeah.
I'll tell you that in the matrix format also, but currently we just think about as let's say if this is the projection, then what is the projection vector? What is the length of this vector, or not length of this vector? What is the vector? All of you know what is the length of vector, right? It's a L2 norm.
Norm. L2
norm.
Okay, not L2 norm. It's basically norm, right? Okay. Yeah, the L2 norm is fine. Okay, just a minute. This is a projection, and what will be this thing? P into A, right?
P.
Or okay, maybe if I'll say that this is some P, and that should be equal to X times A. Okay, that's okay.
Yeah.
And this is a perpendicular over like perpendicular. This is a projection of B onto vector A. Then there is this difference, right? What is this difference called?
Error E.
Error, right? So error in judgment. So what we are saying is that this P is equal to B. We are saying that, like, I'm just saying that P is equals to B, but whether it is true or not, no, right? There is some error between P, the length of P and B, something. If I, this layman terms, if I try to understand, and what is that error? Because it's not a correct vector representation, right? If I add P plus, let us say, if this E, can I get B?
Yes.
Correct, right? I should get B. But what is this vector now?
What is X here? X.
Some
X is
constant.
some constant, right?
Constant. Okay.
Right.
Okay.
Oh, actually, it may not be a constant, but yeah, it's some constant of. But that is basically your projection. It is actually B transpose A. It should be coming as like that, but okay, that is okay. Consider now as a constant.
Okay.
And this is also vector, right? This error also is vector, right? Correct. I'm just saying this E, it's a vector. And if I try to say that B plus E should be equal to P plus E should be equal to E. Is that correct?
Yeah, correct.
And then what is E then?
It is a vector.
B minus P.
B minus.
Now, this understanding is okay?
The vector B minus vector P.
Yeah, because I'm just not saying I'm representing vectors by small letters.
Okay.
And matrix by capital letters. Okay, that's the distinction now.
Capital P is vector, no?
Capital P will be vector. Small p is a so capital P will be a matrix and small p will be a vector. So this is a vector actually. Okay.
Yeah, small p. Here it is a small p.
Small p equals to X times A. Now this relation is fine, right?
Yeah, correct.
This is it's not the thing, right? It's just basic vector addition. I'm just adding these two vectors and I'm getting B. So small p plus E equal to B. I'm using that vector addition here to define E, which is B minus P. But one more thing I know is E is perpendicular to vector A, right?
Yeah.
Or in vector terms, I'm saying that vector E is orthogonal to vector A, right? Or right. So can I say that it is A transpose E equal to 0 because A
Yes,
is
dot product of this
correct,
will
na?
be 0.
Yeah, it is orthogonal to P. That means the dot product between A and P is equal to 0, and dot product can be written as
A transpose
P, right? So I'm just sorry, not P actually. Sorry. E, right? Or E is orthogonal to P. Anything is fine. Fine? Is that okay?
Sir, is it
A dot P.
equal to 0 or A transpose E equal to 0?
Okay. A transpose A equal to 0, or other way around is fine. E transpose A also equal to 0. How will I say that? Okay, maybe what is dot product between A and E? It is
No. What I'm asking is, is it A transpose E equals to 0 or A E equals to 0?
This is same thing. So A dot E, right? Dot product between E. If I use a linear algebra, right? I have to write A transpose E. Why? Okay, I'll tell you why. Suppose
A transpose E is a scalar and A dot E is a dot product, right?
Both things are same. How I'll say? So let us say your vector A is 2 dimensions, right? Let's say 1, 2, and E is also 2 dimension. So let us say, I don't know, maybe 3, 4. Okay. What is 8? What is the dot product between these two vectors? It should be scalar, right? Okay. One thing you know, right? What is the scalar dot product between two vectors? It should be a scalar, right?
A scalar.
Scalar means
A number.
1 cross 1, right? The dimensions should be 1 cross 1. What is this vector?
1
2
into
cross
3
1?
plus 2 into 4.
2 cross 1 and 2 cross 1. When I'll get a scalar out of this, dimensions wise, I should be multiplying this, right? 1 cross 2 with 2 cross 1, then only I'll get the scalar, right?
Yeah.
So what is the transpose of A? 1, 2. If I multiply with 3, 4, then I'll get some scalar, right? So 3 plus 6. Oh, sorry, 8.
3 plus 8, 11.
Right.
3 plus 8.
So this 11 actually is a dot product. So A dot E is a dot product. When I say it's a dot product, but in a vector formats, I have to write like this. I have to take a transpose of one vector and multiply with the other vector. Then only I'll get a scalar. If I just, can I do this multiplication? No, right?
No.
It's not possible, right? So to see, dot product is in vector how to do the dot product in vector representations is A transpose E, but the meaning is same. So A dot E is same as that of A transpose E. Now I think it's clear now, right?
Yeah.
Okay, so yeah, so now coming to that part. So above part, okay, A transpose E equals to 0. What is E then? B minus P?
B minus P.
Okay, how to, like, if I just expand this expression, what should it be? A transpose B minus A transpose
P
equal to 0. Is that fine?
Yes.
Can I say that A transpose B equal to A transpose P then?
Yes.
Yeah. But what is P?
Projection.
And that what is the value of that P by looking at this diagram? It is XA, right?
Yes.
But X is a scalar, right?
Yeah.
When I say X is a scalar, so can I write A transpose B as X into A transpose A?
Yeah.
Yes.
Okay. So if you have some understanding of it, this can be actually is a
Norm of A.
Norm of A, right? Is a norm of A
Norm of, yes.
Norm of A. That means we are actually, what we are doing, we are actually squaring it, that term, right? A square. I can just, if I just have the numbers, if you are not representing it as a vector, it's a square. Square in a vector representation, we are writing as A transpose A. Fine. Is that right?
Yeah.
Okay. So now, what is the value of this x then? Is it A transpose B divided by
norm of A?
Norm of A, right? Or but norm of A should be a scalar, right?
Yes.
And A transpose B is also a scalar, no?
A transpose B also is scalar.
Yes.
Yeah, that is correct.
X is a ratio. X is a ratio.
Of now in this thing, right? Okay, we are not. I'm just saying that only this case. If you go for matrix side, it will not be the same thing. Fine. Just remember this. That's why I'm not writing it in like numbers or something. But now we have found out some x here, right? Okay.
Sir, 1 second. Sir, just sorry. So A transpose is a matrix here, right?
Not matrix here. A transpose A. Okay. A is, let's say, what is A?
Vector. A is a vector.
M cross 1 vector, right? Or n cross 1, something like that. And transpose of it will be what? 1 cross M?
1 cross M.
And what if I multiply that with M cross 1, what I'll get? Output?
1 cross 1. 1.
So that means a scalar, right?
Yes.
This is a vector currently, right? This is a vector A. Vector A.
Sir, 1 second. See, here we are writing P as x times A. So
x is a scalar. Some scalar times that vector
here
A.
x is a scalar. Okay. A is okay. I was okay. Fine.
A is a vector here. X is a scalar. I am just elongating or contracting. Currently, it's a contraction of A, right?
If you want to project 3 on 6, then you have to multiply it by 2. So something like that.
So see, this A is like this one, right? This is the A, entire A, right? But this vector but this vector.
I understood, but I just initially got confused because I was thinking x as a vector and A as a constant.
Oh no. A is a vector. A is a vector. We are just contracting by something, right? Here we have to contract it. Shrinkage constant, like let's say here. We need to find what is that value of x, right? That is what we are actually interested in, and we have found out that it should be equal to A transpose B upon A transpose A. Okay. If I know that x now, what is the projection vector? This, what is P? X into A, right?
P is equal to x into A.
Or can I say that A into X? Same thing, right?
Same thing.
So can I say that it is, or okay, x into A is better. Okay, x into A.
B.
So this should be equal to
B.
A transpose B
by A transpose A into A vector.
Okay, and this quantity was a constant, and constant times vector A is this,
vector.
Right? This
is a vector. Is a vector.
Is a P vector, correct?
Mm-hmm.
P equal to x here, and I have just found out what is x here. Is that okay?
And A and B of the same dimension.
Yeah, that is there. Okay, but that is not we have to worry about right now.
Okay.
But I hope you understood this. What we have done.
Yeah.
We found out
mathematically it is correct.
Yeah, we found out that projection of B onto A, right? That is okay now. This is fine, I guess. All of you are okay with that,
Yes,
right?
yes.
Now consider this as, now what I'm trying to say is, this A is not a vector, it's a space. Okay, just be with me. It may take some time maybe to understand, but yeah, consider this is not a vector A. I'm just saying that this is some space in the sense, now I'm just considering it as a plane.
Plane.
Okay, this is a plane. Okay, so when it is a plane, that means this can be represented by using vector, right? Sorry, matrix, right?
Yes.
Okay, let us say I'm consider there are two components to it. There are two vectors a1, a2. Okay, and column space of, okay, so can you just mute somebody, please mute? Yeah, suppose this is a1, this is a2, right? I'm just saying that this matrix A is a combination of, or it conforms, or it has having two vectors a1, a2 here, and this plane will represent what then? This entire plane will represent what? column space of A, considering this A1, A2 are independent of each other. Is that okay? What is column space of A? It's a span of A1,
A1,
A2,
A2.
right? I hope it is fine. Okay. Right. And let us say this. There is some. I'm not. Okay. Maybe I'll just draw a little bit differently here. This is A1. This is A2. Okay. And I guess you guys understood that this plane is a linear combination of. Suppose this is a linear combination of A1 and A2. And when if you remember, when I say that Ax equals to B is a solution, or when we say that we will get a solution to this when this B is in a column space of A, right? That was the sentence I used, or we made, right? Or the statements we have made previously. Correct? That means if the B was here somewhere in this plane, that solution or that Ax equals to B, it was solvable, right? Correct? And when it is not solvable, when we have some B which is not in column space of A, correct? Yeah, please tell me whether it is correct or
Means
not.
the vector is not lying on the plane, right?
Lying on the plane, it is somewhere else in the plane, right? Like outside the plane, and that's why we are saying that is not solvable. Okay, but we have to somehow solve it, right? Okay, now this is a plane, this is a vector. Okay, can I use the projection method to get a solution to this? Yes, right?
Yes.
So if same thing I have to do, I'm just projecting it here on this plane. Okay, so what does that mean? This vector B is a perpendicular to this plane, correct?
Correct.
And suppose, let us say this has some P, fine. But when I say this B is perpendicular to that plane, and this is P is some projection right now, but we don't have to worry about projection currently. But when I say that this B is perpendicular to plane, can I say that this B, vector B, is also perpendicular to A1 and perpendicular to A2?
Yes.
Yes.
Right?
Yes.
Right. When I say that this vector B is perpendicular to plane, whatever the plane conformed by this column space of A, that same thing, that is the meaning that this is perpendicular to both of them, right? Correct?
Right.
Okay. I hope there is no issue in that. And this vector P is in now, this projection of this vector B onto that plane is in the plane of which is formed by this vectors A1 and A2, or linear combinations of A and A2. Can I say that this is solvable now? Can I find out P? Let us say initially my solution, my equation was Ax equal to B. Now instead of that, I am saying that it is now Ax hat equal to P. Right? This, we didn't have solution for this, right? But do we have the solution for this?
Yes.
Right? But this x and this x hat will be not same. It is different, right? Now that is the approximate solution we call it, but okay, we don't have to worry currently. That does mean is P is some combination of, okay, this x hat, I'm just saying that it is x1 hat and x2 hat. Okay, so can I say that it is x1 hat A1 plus x2 hat A2? Is that correct?
Yeah.
No issues with that? And in other way, can I say that P equal to Ax hat? The same thing. Whatever we are saying till now, it is the same thing. Okay. Now, what is this now?
E
equal to B minus Ax hat.
Ax cap.
Right? What the in a way it is b minus p, right? Because p is a vector
Yes.
here, b is a vector here, but this p, I said that p is nothing but this. Okay, maybe I'll okay. And one more thing is this E is perpendicular to P, right? Or what else? Can I say that this is perpendicular to A1 and A2? So A1 transpose P should be equal to 0. So, sorry, not P. E should be equal to 0 and A2 transpose E should be equal to 0, right? We are fine until this point, okay? Okay, and A1 transpose, what is E? I'm saying it's B minus Ax hat.
P.
Or B minus P, or I'm just saying that P is Ax hat equal to
Correct.
0 and A2 transpose B minus Ax hat equal to 0. Is that fine?
Yeah, pardon, sir. Once again, this
Okay.
A1 transport.
Okay.
I
What
could
I'm saying,
not get it.
yeah, what I'm saying that this E, right, error vector,
Yeah.
is it perpendicular to this P?
Yes.
Okay. But what is P now? P is
Ax
Ax hat.
Ax hat.
Okay. And that means E, what is E now? B minus Ax hat.
Yeah.
Right. I'm substituting this P here.
And this X hat is the linear combination of the A1 and A2.
No. X hat is this vector, na? X1 hat, X2 hat. This is the solution we are trying to find out, right? This is the vector.
Okay.
Vector. Okay.
X1 and X2 are two vectors.
No. This X hat is a vector. X1 X hat and X2 hat are the coefficients, right? The constants.
Yeah. X1 hat and X2 have X2 has a coefficient.
Yes. So why they are coefficient? Okay. Let us say P is in this solution space, right? That means in the plane. What does that mean? It is in the span of A1, A2, right?
A span of A1, A2.
Okay, that means P should be okay. I'll write it down.
P should be represented.
P should be in span of
a span
A1,
of
A2.
A1, A2.
Right? Is that okay?
Yeah, correct.
What does that mean? What does that mean? P should be a linear combination of this, right?
A1 and A2, correct.
What I'm saying that this linear combination is X1 hat. X1 and X2 hat are some constants.
Okay. Constant, not vector. Okay, got it.
Right? X1, X2 hat are the, and what we wanted to find out, we want to find out these points actually. But if I write them into a vector, it will look like that. Right? In the matrix format, how should I write this? P, or in the vector format? It should be
A1, A2 as columns.
Yeah, it is.
What does that mean? X hat transpose.
X hat transpose.
Actually, these are not vectors basically, right? If they are columns, so this will be okay. But now, okay, don't worry about it. Like, let us say these are some values. Basically, they will be like this, no?
Yeah.
Right? Okay. So this, you understand the point. So it's not a main point, but what I'm trying to say is this P can be represented as the linear combinations of this, and these are some constant, let us say. Right? And we are trying to find out, because if you find out these values, then I'm able to say that this P is in the solution space, right? If you understand it properly now. Okay, that P is there. So this error vector can be represented as what? B minus P. I'm just saying that it is Ax hat. Right? Now E will be equal to B minus P. That means E equal to B minus
Ax hat.
And what is X hat? It is basically, it is a vector of this, right? Okay. I hope this is fine. Until this part is okay.
Okay.
And does that mean this E is perpendicular to the plane? That means E is perpendicular to both A1 and A2, right?
Correct.
And that I can write it as because that means they are orthogonal to each other. So A1 transpose E equal to 0 and A2 transpose E equal to 0. So A1 is a vector, E is also vector, A2 is also vector, and E is also vector. So I can write these two equations. Okay. I hope this until this this part is fine. But and what is the value of E? E is basically B minus AX hat.
B minus AX hat, correct.
Okay.
Correct.
So I'll get these two equations. But can I combine these two equations to represent all of these things into a vector format or matrix format? Can I say that this A1 transpose here, or okay, not like that. This is a vector basically, but yeah, A2 transpose here, and I'm just saying that it is B minus AX hat equal to 0.
Absolutely, we can.
Yes.
This is okay?
Yes.
Yes. Yes.
You can just multiply these things and you will get the same thing, right? We'll get two equations. Fine.
Yes.
Correct.
Right? This is equation 1 and let us say this is equation 2. But we are getting, are you able to clearly see that this is the thing? Right.
Yes.
Sir, A1 transpose itself is a matrix and A2 transpose
No.
itself is a matrix.
This is a vector. This is a vector. Na? What I said, A is what? A is formulated by these two vectors. Na? Right? Matrix A. I am representing matrix by capital letters and vectors by small letters.
Okay.
Okay? Done?
But
what I said.
Then what do you mean by transpose of a A1? A1 is not a matrix, no? A1 is a
vector. We can take a transpose for a vector, right? Can you not take?
Yes, we can.
Is that fine? Okay.
Sorry,
Okay. Let us say you have this vector 1, 2, 3. U is a vector. What is the transpose of U?
No, I mean, okay. But then what does that mean? I mean, so I am reading 1, 2, 3 as a matrix here rather than a vector. Is that wrong?
Okay. What do you do in matrix transpose? I see. Let us say you have A. You have a bunch of values 2, 3, 4. Suppose. Okay. That's
A
okay.
transpose is columns will become rows and rows will become columns.
Okay. What will be that 1, 2, 3, 2, 3, 4, right?
Correct.
Okay. Let us say this is some A1. Let us say this is some A2. Can I say that?
Yeah.
What is the transpose of that?
Okay.
Is it okay? Or can I say that like this?
Okay.
Done?
Okay. Yeah.
That's fine, right? So if I am representing this, what does that mean? Is it not A transpose? Are you able to connect now?
Yeah. I think
See, this is 1, 2, 3, right? And this is 2, 3, 4. What I'm saying is A1 is 1, 2, 3. A2 is 2, 3, 4. Fine, separately. And when I write A transpose, what I write here is 1, 2, 3. Here 2, 3, 4. Fine. So what actually I done is I have just taken the transpose of it 1, 2, 3 and A2 transpose as 2, 3, 4, and I just represented into some matrix format like 1, 2, 3 and 2, 3, 4, and I'm just saying that it is a transpose.
Yes.
Fine?
Yeah.
Yeah. Sure.
This is what is it? You just don't think about it like every time geometrically. Just think about like we are doing some operations, right? We are just representing all these vectors into some format, and we'll try to do some operations irrespective of what. But whatever we are doing is not legally incorrect, right? Okay.
Yeah.
Okay. So now I hope this is clear.
Yeah.
Okay. Give me 2 minutes. Okay. A transpose. Can I now say this as A transpose?
Yes.
A transpose into B minus AX hat equal to 0. Can I say that? Or maybe
Yes.
0, 0.
Yes.
Right? Now if you remember all the things, our all understanding till now will come here now. What we said is AX equal to 0. If this equation is satisfactory, then this will be represented as what? Null space.
Null space.
Null space. Null space.
And if it is A transpose X equal to 0, then null space of A transpose, right?
Yes.
So this is basically what is E, and it is actually a null space of
Null
A
space.
transpose. Just a minute. You can take it here. Yeah. Right? Sorry, I just now you can just able to this fine, right? This part. So we can say that this error vector is perpendicular to null space of A transpose. That's okay. Okay, this understanding is not required right now, but
we already started with the same.
Yeah.
We did projection.
Yeah.
Which was itself perpendicular.
Correct, and that is what we are actually trying to see now currently, right? But
mathematically, we are representing mathematically. It is correct, right?
Yeah. Yeah. Now, can we just do some manipulation as we did for vectors here? So if you expand these terms, what I'll get? A transpose B
minus A transpose into A transpose into A is equal to 0.
That means
A
A
transpose B.
transpose AX hat equal to A transpose B. And if you remember it from the previous thing, we tried to find out this, right? X, y. We need that constant to get the projection vector, right? Because it constant times that vector A was the projection vector. What here in the matrix format, what we tried to find out? Some combination of all of this. If I multiply it with the vectors A1 and A2, I should get something, right? I guess it is fine. If you initially
X hat is equal to A transpose B upon A transpose A.
Yeah. So what I'll get here now? X hat will be equal to
A transpose B upon A transpose
A transpose B, but it is not A transpose A now. Why? Because this is the matrix, right? In the matrix, we can't do that. What we should do then? We should go for inverse.
Inverse.
I hope all of you are okay with that part, right? What we should do now to get X hat here, I should multiply here with A transpose A inverse on the both sides, and if you know the rules, it should be like that, right? You cannot just multiply anywhere. If I'm just multiplying on the left side of the matrix, right, the same thing I should do in the right side. That okay? I hope all of you are fine with that. And so this is one matrix, let us say some C matrix. This C inverse. So C inverse into C will be what? If you know the property, it will be an identity matrix.
1, 1.
Identity matrix, right?
I.
So then X hat equal to, so I into X hat is basically, you'll get the same vector, right? So X hat will be equal to what? A transpose A inverse into A transpose B. Is that okay? Or I can just, if I can just, so this is my X hat, and what I need now, this was some initially what we did there, the previous case, we find out the projection how? If you just multiply, because projection is on that vector, right? A. So what we try to find out X, and we just multiplied with that vector, so to get the value of projection. Is that correct?
Correct.
But here, yeah, but here
Dot product, no?
Dot product, yeah, you can say, or just like multiplication of, right? You just multiplied this constant with that vector A to get my projection, correct? Projection vector. But in that time I said x was a scalar which I multiplied with that vector A, then I get the P. But if it is a two-dimensional case, in this case, what it will be now? That x will be x hat, or in that case, x hat will be a vector, right? It will not be a scalar, correct? X hat is, what is that? X hat, basically this thing, right? Right. So but still I need this P, right? I need this P. So can I say that x1 hat into a1, and we have to say x2 hat into a2, something that combination will give me now P, right? Is that fine? See, this is what we started, na? Now we found out some x1 hat and x2 hat. So what will be my projection P here? But then it will be a matrix, right? I'm just denoting it as a matrix now. Capital P equal to some exact vector into which one? B, right?
Yeah.
Vector B. Right? I hope it's not going to bad. No, right? Sorry. It should be equal to AX hat. Sorry.
A1 into na?
AX hat. Sorry. A1 into X. Sorry. Because we need that combination, na? Now. A1 X1 and A2 X2. Fine. I hope this is okay. So this is my vector then, right? This is a vector. It's not a projection matrix. This is a vector. Fine. I hope it is okay. What is AX hat here?
Yes.
Is A1 X1 plus
A1,
A2 X2 or hat in that sense. Fine. But then what will be P then? A times X hat. What is X hat? This portion. Inverse A transpose P. I hope this is okay.
Yes.
Oh, okay. No, it's no. I hope this is fine, and that is your solution actually. This is your projection vector, and in that case, this thing, right? This part, this portion, this portion is your called as projection matrix. Okay, so this projection matrix, if I multiplied with vector B, I'll get the projection P,
which is a vector, na?
Which is a vector.
A small p, na? It is a small p.
Yeah, it is a small p. So it is a projection vector. You understand, right? See, this is a B vector. This vector. This is basically a matrix, and this matrix is called as a capital P projection matrix. And if I operate that projection capital P matrix onto vector B, I'll get a projection. If you try to understand here, okay, maybe I'll just draw a fresh diagram to understand it better.
And where A is there, where is the matrix?
A was the matrix of, like, so A is basically this
column space of column.
A is a which contains vectors A1.
A span of A1.
This plane is representing a span of A.
Yeah.
Right.
Yeah.
Now I said that there is this vector B, but it was not a solution. I need to find out the solution, and I will find out the approximate solution by, projecting that B onto this column, this plane, right? And that approximate solution was vector P, right? This vector P. But now what I'm saying is this P is some combination of this A, and this P equal to, because see, this P should be equal to, like, we just have to find out some relation, right, between B and P, and that relation is given by the above value, and that should be equal to what? A into A transpose A inverse A transpose
A inverse into A transpose B.
Okay. But okay, so you don't have to worry about all of this equation and all. How to find out the solution to this problem is lies here.
And this will be this just go down. This formula.
You don't have to remember. Okay, it's just I wanted to find it out, that projection P. What is the value of projection?
What I'm telling, this formula A into A transpose A inverse into A transpose will give a scalar value, no?
No, vector. This part you're talking?
Capital A matrix A into A transpose A inverse into A transpose.
It's a matrix.
This will give a matrix, no?
Yeah, it's a projection matrix.
Okay.
Times
This matrix
vector.
will be matrix times vector will give a vector, right?
Correct, right?
Correct. Okay, fine.
You can just find out the dimensions later on. It's like you can find it out. But now how to solve it, right? But okay, so that's okay. This is for to solve that computer. But how we do manually, right? How will you solve it manually? So that lies here. This part. This part is fine to all of you.
Yeah.
I hope I'll just write it down again. What we said is A transpose into that vector E equal to 0. So that means A transpose B minus AX hat equal to 0, right?
Yeah.
Can I say that A transpose B equal to, or maybe I can just say that A transpose AX hat equal to A transpose B. Is that fine? Let us say I just say something like this. Suppose, how to solve this? Can you look at like this problem Ax equal to B? How to solve this Ax equal to B problem? How we understood it?
If B lies in the
find out A augmented B.
A augmented B.
And
yes.
then we just do some multiplications, and then we just multiply with that vector. I was able to find out that, right?
REF. You form the REF form then.
So in this case, A transpose A is a matrix. A transpose is a matrix, and this B is a vector, and X is a vector, right? This is a matrix. This is a vector. This is a matrix. This is a vector, right? Right? How to solve this then now? This equation. A transpose A augmented A transpose B, right?
Yes.
Or else if I just take a common, actually, okay, I'll just show you that final understanding. So if I just multiply A transpose to A augmented B, right? Then I'll be able to solve it. I'll show you how. I hope this is clear, right? Until this part is clear. Now I'll take just 10 minutes and we'll finish it off.
One example is.
Yeah. So we'll go for least square methods. Okay. Where does this least square method is used? Fitting a line, right? I hope you understand. You know linear regression, something like that. I'm just taking
least square.
Yes. Linear regression.
Right, no? Yeah. 1, 2. These are the two. Let's say these are the values. Suppose there are certain points. Okay, one point here, another point here, and another point here. Okay, I'll tell you the exact values of these points. So suppose this point is, what do you think this point is? What is the coordinates? 1, 1?
Yeah.
Yes.
2, 2.
This is
3, 2.
2, 2.
2, 2.
And this is
3, 2.
3, 2. Right? If I wanted to fit a line to these values, right? What will be the equation of this line?
Y is equal to X.
Or here I'm just using D and T. Now in this term, D equal to
D is equal to T.
And some here it is
empty.
No, there'll be some slope.
Plus some constant.
D is equal to MT plus C. D is equal to some M slope into T
plus
C.
C,
plus
right?
C.
Something. Okay.
Y is equal to MX plus C form.
Right. Okay. Is that fine? So if I use that, but do you think that all these 3 points are on the line?
No.
Right? So what to do then? Can we project these points on that line?
Yeah.
So whichever points are not on the line, we'll try to project out on the line and we'll try to find out the solution. So this is same as that of we used earlier, right?
Correct.
I hope that is okay.
Yes.
Okay. Now just try to understand this part. If I am saying that this is the equation of line, how should I represent this point on the line? D.
Which point?
This one, first point. Can I say that it is equal to C plus D equal to 1? I don't know C. Do I know T?
No.
T is I know, right? 1.
T is 1.
So T equal to 1. Okay. What we are trying to do here is the equation of this line is D equal to what is it? Mx plus C. So that is M T plus C. Right? So for x equal to 1 or for T equals to 1, what is the equation here?
M plus C.
M plus C.
Yes.
Think it again.
M plus C is equal to 1.
Yeah, basically, actually, okay. So let us say it is M plus C equals to 1, or M plus C equals to 1, or okay, in the matrix format, how should I write it? Okay, leave all of these things. If it is a matrix format, if I wanted to solve this equation, can I say that it is some C plus okay, let us say x and y here. I think that will be better to understand this part. So I will say that y equal to mx plus c. I'm just saying that this is the equation of line now in our understandable purposes. So any point will be for x equals to 1. What is the point? M plus c.
Y is MC.
1. What is equal to 1 here? That is a true value, right? That b vector.
Yeah.
Right? We are actually trying to fit that line, right? Through all these points.
Okay.
For x equals to 2, 2m plus c equal to how much? 2, right? And then for the third here, it is 3m plus c equal to 3. Is this a equation of, or is this equation we try to fit in?
3 or 2 is it? Your y is 2, right? For the third equation.
For third
No,
equation, 3m plus c is equal to 2.
2.
No, it is correct. 3m plus c is
Yeah,
equal to 3.
sorry. Yeah. Right? So this is the equation we are, so is it soluble? Actually, by looking at it, is not soluble. Soluble means what? All these points should lie on that line, right? Which I drawn. That is not the correct thing. But it can be solved by using the, let's say, matrix format. How it will look like now? Can I say that, okay, just try to see that CCC on the one side. So let us say I'm just writing these equations as C plus M, C plus 2M, and C plus 3M. Okay, now can you tell me if I wanted to see these equations in a matrix format, which is AX equal to B.
1, 2, 3, and
1, 1, 1,
1,
2, 3, and
CM.
What are the values we need to find out? Solution for CM.
CM is equal to
1 to 2. Is that right?
Correct.
Is this by okay? If you don't know, is it solvable or not? Can you tell me whether this solution exists here? Can we able to find out the values of C and M such that this will be true? That means this B should be in the column space of A. Is it possible?
Yes.
Not possible, right?
No.
Not possible. You have only 2 variables and 3 this thing. So.
Why it is not possible?
Rank is 0 for B.
Rank is what? Okay, what is the, okay, how to find it out?
It won't be full rank basically.
Not full rank, it doesn't matter, right? If it is infinitely, the both rank should not be same. Okay, I'll try to.
Yeah, it won't be.
So if what operations I should do? I will make it 0. sorry, I will make it 0. So it will be 1 and 2, right? What operations I did? R3 changes to R3 minus 2R1, R2 changes to R2 minus 2R1, right? And augmented matrix, what happens here then? 1, 0, 0, right?
Yes.
R2 minus R1 it is, not 2R1. But yeah, we get the point, yeah.
Okay, sorry, yeah, that's fine. I think we should make, sorry, I think, okay, first
Yeah,
point is, okay,
yeah,
first thing is we should
we
make it
understand,
0,
yeah.
right? Okay, I did make, okay, and then what is the next thing? I think, yeah, that's, I
Yeah,
think
you can make
that's good.
you can divide the bottom row by 2 and just have the bottom row as 0, right? It will be a row full of zeros.
What I have to do next is I have to
Like,
just,
you can divide
yeah,
it. Yeah, sorry, not yeah, not
I just
Yes, done.
subtract. I have to subtract, na?
Yes, done.
This is the final answer, right?
Right.
Or should I do all the operations?
No,
Okay.
No, that's fine. That's fine.
It's
That's
fine, right?
fine.
Okay. I because that and what is the now? This is A, and this is A, and this entire part is A augmented B, right? What is the rank of A?
2 and 1.
2, and what is the rank of? Oh, okay. Sorry, this will not be the case, right? I think what will
Yeah.
happen? I just made it 0, 0. In that case, first operations will be what?
First will be R2 minus R1 and R3 minus R1,
R2
right?
minus R1, then it will be 1, and then yeah, then I had 2 here.
1 to 1 to 1 to
1, and then
first
make it
1 1 1. It will be there.
Yeah, and then no, after that you'll have more operations, no?
I have to make this as pivot, and then I have to
Yeah.
make it as 0.
0.
So after that, this will become -1, right? Okay.
Yeah.
Then the rank of A augmented B will be 3, and these two are not equal, and then that means it is not solvable, right? Then I cannot get this values of C and M, right? Okay. What does that mean? The columns.
Yeah, the augmented matrix will have a full rank, right? I mean, it will have all 3 pivots, right? Have I got it right?
No, we don't have to go ahead again, right? We just
No,
have to
we don't have to, but I'm just saying.
Yeah. Okay.
Since there is
it may
the
have,
difference
it may
between
not,
the augmented, yeah, the difference between the augmented and this thing, the rank, 1 is 3, 1 is 2, right? That's what I'm saying.
I think, yeah. Okay, that is
follow.
okay. That is okay. You just do it calculations. Calculations I'm not bothering about now. What we are
Sure.
Can we just say that this B is not in a column space of A? I think we can look at it and we can just say that it is not, because this two, right? So you can just do the calculations later on. But by looking at this vector and the column space of A, because column space of A is what? It's a linear combination of 1 1 1 and 1 2 3. But that 1 2 2 will not.
But when you look at the figure itself, you know that
correct. It is not
the 2 points.
Yeah, you don't have to solve the whole thing. Yeah,
3, 2 are not in line.
Okay,
so they will not follow that equation.
Right. So basically, what I'm trying to say to you is that this B is not in a column space of A. Why I'm saying it like again and again is that means I don't have the solution for this Ax equal to B, and that means I will not be able to find out the true C and true M, right?
Yes.
That is what I'm trying to say. So what we do we try to find out the approximate solution, and to find out the approximate solution to this problem, we have to project. We have to use the projection matrix, right? That space. And what to do now? And then will I get C and M, or will I get C hat and M hat as a solution?
Yeah, there will be some error, no? You will get C hat.
Right. Yes. And we'll find out now. So I'm trying to show you the answers. So what I said to you previously, how to find it out? We can use this thing, right? We'll use this part. Is that right? Okay. And what is that? A transpose Ax hat Okay, A transpose Ax hat equal to A transpose B. Is that fine? And how to solve this equation is, what is A transpose? Can you tell me what is A transpose?
1 1
1 1
1
1 1 2
1
3.
2 3.
And I'm just saying that you use the A augmented B like we did previously. Is 1 2 2. Okay, is that okay? Is it giving me the same thing here? So if I multiply this part with this part, I'll get A transpose A, right? Because
A transpose A?
this is A transpose, this is A, and this is B. If I multiply A transpose A, like if I multiply these values to that part, I'll get this part, na? A transpose A, and this with B, I'll get this part, right? Basically, so solving it as like Cx hat equal to some D, right? And what is C? C is A transpose A, and what is D? A transpose B, right? And how will you solve this Cx hat equal to D? Just by looking at the ranks of C augmented D, right? So maybe D is like that because vector, right? I hope it's clear. Okay, so how to do that now? How to solve this?
Yeah, that part, just a minute, this one. A transpose is okay. And A is the matrix 1 1 1 and 1 2 3. 1 2 3. Okay. And X hat is?
X hat we have to find out. No, this is we have to find out, right?
Okay, that is variable.
Yeah, that these are the variables. What are X hat?
And A transpose B is 1 2 3.
X hat. Huh? No. No. B is 1 2 3. 1 2 2. Right? You look at it, na? B is 1 2 2.
And where is the A transpose then?
Here A transpose A. If I'm multiplying this A transpose with this A augmented B, I will get the same things. That's what I'm trying to say. No?
Yes.
Okay, you guys can later on check it. If you if you find any difficulty, I'll
okay, I will check it.
Yeah, A transpose A is what? Can you now just multiply here first?
1 with 1.
3, right?
3.
Then here I'll get 1 plus
1 6.
6.
Here
6 and
1 plus 4 plus 9.
5 and 9.
14. And here 5 and 1 plus 4 is 5. 5 plus 6 11, right? I hope it is okay. And this is actually A transpose A, this part, and this part is A transpose B. Fine. And how to solve this now? Basically, I'll get two equations: 3C hat plus 6, or okay, how we define C and M? Okay, then CM hat, 6M hat equal to 5, equation 1, or 6C hat plus 14M hat equal to 11, equation 2. We can solve like that, or what else we can do now? We actually can go back like to reduce rows.
RREF, yeah.
Not
Gaussian
RREF.
elimination. Yeah, Gaussian elimination is sufficient. Yeah,
sufficient, and we can get it right. So what I'll get now by
These are similar to.
Yes, that is what I'm saying. That is similar to this, or whatever the solution we have initially said.
Simultaneous equations, no?
Correct.
By simultaneous also we can solve.
Yeah, now I'm just solving it by simultaneously only. So it is 2 times or something. If you do it, what I'll get? 2M hat equal to sorry
1.
2M is equal to 1.
That is M hat equal to 1 by
M
2.
hat is equal to half.
And what is C hat equal to? You can actually substitute 1 by 2 here, like in the above first equation.
2 by 3. 2 by 3.
right? Na?
2
5 minus 3.
2 by 3.
You just substitute that m by equal to r.
C is equal to 2 by 3.
Correct, right? So now this is my solution, right? This is, I am calling it as x hat, which is c hat m hat, which is 1 by 2, 2 by 3. What does that mean? Initially, what is the equation of this red line now?
Y is equal to mx plus c will become
1 by 2.
Y is equal to half into x plus 2 by 3.
Right. Now, is
That
that
will be
fine?
the equation of the line.
Like,
Yes.
but will that represent my all the data points? No, right? It's an approximate solution. Is that
No.
right?
It
Correct.
is approximate, yes.
Okay.
So we will have to
Find out the errors.
find the errors.
How to find it now? Will you do that? It is easier, right now? No?
Yes, C hat and
We
M
now
hat is
we
C
know
hat,
now. Yeah. So what
C
is the
hat M
equation
hat.
now?
Okay, CM. Okay.
Yeah. What is
Variables are there.
it? Is
Right.
half x hat plus 2 by 3, right? Or x hat or
2
x.
by 3.
Now, how to find out the errors is you just plug in the values of like x equal to 1. What is the value of y? Y hat 1 by 2 plus 2 by 3. Right? What is that?
Okay.
3. Can you tell me what is it? 3 plus 4, 7.
10 by 6.
7,
7
right?
by
Yeah,
6.
3 twos are, yeah, 3 ones
7
are
by
3.
6, right?
4, 7 by
And
6, yeah.
and what is the error here then? For first calculation, error 1 is equal to, it can be like anything. It can be 1 minus 7 by 6 or 7 by 6 minus 1, however you want to take. So I'm just taking it like this. So it is 1 minus 1 by 6, right? Why 1? That is a true value, right?
True value is 1, correct.
Correct.
What about x equal to
C
t?
plus m is
X
equal to
equal to
1.
2. What is y hat for x equal to 2? I just plug in here 2.
2.
So 1 plus 2
1
by 3.
plus 2 by 3.
How much it is? 1 plus 2 by 3 is 3 plus 5. 5 by 3, right?
5 by 3, 5 by 3.
So it is 2 minus 2 by 3. So what is
2
it?
minus 2 minus 5 by 3, no? Y is 2.
Oh, sorry.
2 minus 5 by 3.
1 by 3.
1 by 3.
Right? And what is it? That this is what? Error A2. And you can similarly you can find out the third error.
Okay.
And what will be your error vector then? Minus 1 by 6, right? 1 by 3, and I know the third value, so I'm just writing. I think now you guys know how to find it out. So it is minus 1 by 6. What is my vector b? What is the vector b? 1 to 2, no?
1 to 2.
Right, na? I hope this is fine. And then what is p now? P is? Okay, what is b? Is there any relation equal to b equal to e plus p plus e? Okay, we know that, right? What is e equal to b minus p? That is fine.
B minus P, the error relation, yeah.
Then now, what is the vector p?
B minus E.
B minus e, right?
So
Yeah.
how did you get 7 by 6?
Right? No. Okay. I think, see, it's like a lot in one day, so that's what it's fine. But I understand. You understand now. Whatever the vector you get p vector, that should be equal to what? Can you tell me? That should be equal to this, right? A transpose A inverse A transpose into B. You can just find out if you get time. You just find it out. It should be equal to P.
This should be equal to that.
Right, because we have just followed the same things, but in a different way. In a way, we can solve it. I hope this least square method is also fine for you. Whatever doubts are there, we can just take it later in the late sessions. But I hope this is fine. I have tried to connect all of this. This may, I don't know. This may be understandable right now, later on, or somewhere. I'm not sure, but yeah. I hope certain things as clear to you. Why we need projections? Why we go for projections? Why not the earlier methods? Right? I didn't go into that row reduction and RREF very detailed because I am assuming that all of you know that part. Fine. I
Sir,
hope this is
here the C hat value is 2/3, but it is mentioned as half. That should be interchanged, no?
C hat is 1/2 and M hat is 2/3. This is a proxy value, right? Approximate.
No. At the bottom, the last end, it is just, I think it is opposite is written. Yeah, here C hat and M hat is should be
Okay.
2/3 and half.
Yeah. Sorry. Yeah, you just do it. Sorry. Yeah, not like that, right? You just use this value.
C hat is 2/3.
Sorry. It's okay. Yeah. You are correct. It should be 2/3 and 1/2 there. Shall we close it now? Like it's a very long session, so but I just
Yeah. We should close. We will do it again.
Yeah. You just go through it again.
Yeah.
Whatever I done, I just try to
So
see that.
even E2 and E3 are found by this minus 1/6, 1/3, and 1/3.
Actually, we have found out that solution which gives me the value of that projection which lies into that span of A, right? Initially, why we were not able to find it out? Because that was not in a span of A, right?
Yes.
This B was not in a span of A. And if it was
So
there,
we found the approximate
solution. If this B was in that span of A, the solution was this, na? C and M.
Yes.
Correct?
Yes.
But that will be the exact solution. But this is not a case.
Then the third point should have been 3/3.
Correct.
3,3.
Yeah, but that is not.
That would solve the equation.
Correct.
But
that is again go back
because
to your.
we have 3/3,2. That is why we have to find the solution.
But you understand now
yes,
why this is needed. If you see, this is the
Yes.
real world problem, right? Because in real world, we will not have all the data points on a single line.
On a line.
Right. In that case, how the people solve that problem? By projecting it.
By approximation.
Right. And that is the projection is the correct
projection
method.
of.
And we will deal with that like again in week 7 when we learn about PCA. But yeah, this is what I wanted to show it to you. I hope it is fine. I am not sure like whether all of you understood. There may be some people who will say not good and all, but okay. It's okay. I hope you enjoyed it throughout. If I done some mistakes somewhere, I'm not sure. Maybe sometimes while speaking or writing, I done some mistakes. But
no problem.
It covered the week 3 all or
yes.
something?
Yeah, done.
Oh, okay. Thank you.
Okay, guys. Thank you. Bye.
Okay,
Good night.
thank you. Good night.
Bye. Good night.